All right, so today we are looking at day 4 of PFT 105. This is going to be our cardiovascular system. So we are going to talk about, we talked about energy and how we produced it. Then we talked about how we extract energy from food. Then yesterday we talked about how we extract energy from oxygen. And today we're going to talk about the taxi cab that carries all this stuff around. Right, we're going to look at our cardiovascular system today, which is the system responsible for, delivering all of that oxygen that we talked about. The energy system that's responsible for delivering all that glucose that we talked about. And the system that's obviously also responsible for removing all of our waste products so that we can start that whole process over again. So when we talk about, our objectives today are to, understand what constitutes our cardiovascular system. So when I say cardiovascular, like what anatomic pieces am I talking about, and then we want to talk about like what their functions are, so we're going to be talking about the heart, blood, and blood vessels today, and how each of them perform. We'll talk about one of the cool things that we'll talk about is how electrical excitation happens. Basically, your heart is one of the coolest organs you've got in your body because, I kind of mentioned it briefly yesterday, and you guys probably know, your body is coordinated entirely by like electrochemical signals. Like your body generates an electric charge by moving some stuff around, and it's kind of like static, like you're like a little static electricity factory, and all of your cells are generating a little bit of this electric charge. That's why, like, you can, if you ever had like one of those lights, my roommate had one when he was growing up. I remember my roommate is a friend of mine from high school and stuff. And it's like those lights where if you touch them, it turns them on. It doesn't have like an on switch, and you can touch it and it gets brighter. And, the way that happens is you've got like a passive little electric signal like running through your body. And so you pass some of that off and it was able to signal the light. But what's really cool is like all of that energy production, all of that electricity production takes energy. It takes energy to like move stuff, it like and create that battery. Your heart, don't get me wrong, it absolutely takes energy for your heart to do that as well. But what's so cool about your heart is that your heart, by pumping, sort of recharges itself just a little bit. It's able to kind of keep itself on its own rhythm, and it's able to keep itself, producing that electric charge simply by beating, because your heart actually leaks a little bit. Not blood or anything, but it leaks these materials that create that electrical excitation. What was that?
No, that you were saying about they will produce electricity, right?
Yes, electricity. Yeah. So that's actually what we're going to look at that. That's called electrical excitation. And we'll talk about how it's spread through the heart and allows that to happen. We're also going to talk a little bit about cardiac output. Actually, we're going to talk a lot about cardiac output. Cardiac output, the overall, how we as, health and fitness professionals, is how we measure the overall performance of your heart. Like, is your heart performing well or is it struggling, right? And so we're going to talk a little bit about that cardiac output, We'll talk a little bit about like what is maximal oxygen uptake. So that's where we're going to kind of pivot the conversation into talking about like oxygen consumption, right? And then we will talk a little bit about like, do you have a high cardiac output? Do you also have a high VO2 max? What does that mean for performance? And that's where we'll kind of, at the very end of today's lesson, we'll kind of get into like the conversation of like, what does it mean to do a cardio workout? Like, how do you improve it? Why do you need to improve it? Why is it important? And things like that. And then we will talk about the concept of this respiratory exchange ratio. The idea of how much oxygen's coming in versus how much of it's being used. Are your cells really efficient? If they are, they're going to consume a lot of oxygen. They're going to be like, oh, great, I can use that. Boom, and they're going to turn around. Or are your cells not so efficient? Does that oxygen come in and then not get used? And then there's another learning. Oh my God, there's 4 pages of learning objectives. And then we're also, sorry, we're also going to, oh yeah, of course. So we're also going to describe how this part of your heart is under the control of your nervous system. particularly those unconscious nervous systems, either the sympathetic or the parasympathetic. That's the fight or flight or the rest and digest sections. And then we will look at how coronary arteries are slightly different from regular arteries. And then we'll talk a little bit about blood pressure as well. So, lot to talk about today. I like talking about the heart. I think the heart's always kind of fun because it's really just like, it's as close as, I don't know if how many people were in which class or which class I said it in, but I always meant to like learn about cars and I never did. I always meant to like, learn how to like change my own oil and I just never learned how to do it. And be like self-sufficient. But the heart feels kind of like a car. I know a lot about the heart, so it's got a lot of like working pumps and pieces to it, and like you got to know how all those pieces kind of fit together and what they each do and all the different chambers and stuff. And so I always like talking about the heart because it feels like it's how I traded out like my knowledge base. So looking at the cardiovascular system, right? When I'm talking about the cardiovascular system, what I mean is it is your heart, your blood, and your blood vessels. And when I say blood, we touched on this just a little bit at the end of our lecture yesterday. I don't just mean red blood cells. I mean everything that's in actual blood. And blood is not just red blood cells. It's got all of these other constituents as well, right? It's got your red blood cells, right? At the very bottom there, there'll be a little thin layer of platelets and white blood cells. That's your immune system that's in charge of like killing foreign invaders and viruses and bacteria and things like that. And then a lot of it is plasma. And plasma is made up of a lot of like water. It's got electrolytes in it, which we're going to talk a lot about today because that's what's creating those charges that I mentioned. It's going to have glucose and fats and proteins, and then all that stuff that's getting carried around that needs to be delivered to all the various parts of your body. So the heart, blood, and the blood vessels, it is the system responsible for providing a delivery system of nutrients. And nutrients we're going to refer to as like, all of our macronutrients, and then we're going to throw oxygen in there as well, throughout the body, and generating and maintaining pressure. And that part right there is, very similar to how pressure was very important part of our conversation yesterday, right? We create an area of low pressure, and so air rushes into our lungs. We create an area of high pressure, and air rushes out of our lungs. Well, your heart is responsible for generating pressure inside of your body, because here is where we are finally pivoting. We were very much outside the body when we were talking about the digestive system. We were kind of outside the body when we were talking about lungs. Now we are very, very, very much into the tissues and the blood of our body. This is what we refer to, sometimes you'll hear it referred to as being systemic. Our conversation is systemic now. It's in the system, right? And the system is you. So we are in the you, right? And so what's interesting is like your blood vessels, right? Your cardiovascular system is a closed circuit. Like it's a series of loops, it's a series of tubes, and they're all connected to each other. And like, at the end, like if you were to move away, well, guess what? It comes back and connects to the other side. So it's a closed circuit. And, those blood cells can kind of pass and grab stuff and get back into that circuit. But for the most part, this is the very much like inside part of your body, like in the most literal sense. And so, if we want to be able to move stuff around a closed circuit, we need to be able to generate and we need to be able to maintain pressure. Because if we can't generate pressure, there's no way for me to get blood to pump up against gravity to get to my brain. And if I can't maintain that pressure, then all of that's just going to fall straight down and it's just going to all flood my legs and it'll just be stuck there until I like flip my head around, we'd have to like spend our day, like if we didn't have like this closed circuit and we didn't have a heart that was able to maintain pressure, you'd have to alternate standing on your head versus like walking upright all day long just to move blood around your body, so luckily that doesn't happen for us. So the roles of your cardiovascular system, like, what is it responsible for? What does it do? Well, it's going to help you regulate and maintain body temperature. That's one of the cool things that it does. We love talking about that, actually. I love talking about that. It's always kind of a fun one, right? Like when you think about like the idea of your body temperature, you know, when you are getting really hot, for example, you know, your body has all of these really cool processes that it will do automatically without your control. Like, so you start getting really, really, really hot. What's going to happen is your skin, your blood vessels are actually going to expand and they're going to move closer to the surface of your skin. And what that does is that actually allows when air rushes past like all the little hairs on your arm, or if you happen to be sweating and you've got like liquid on your arm, when air rushes past that, it's going to get really cool. And now because blood is closer to the surface of your skin, it's going to grab that cool temperature and it's going to carry it throughout the rest of your body. And that's why we sweat. That's why, you know, when you're hot, you actually, when you're working out, you feel hot. Like you touch somebody, you go shake somebody's hand, and you're like, they're like, "Good God, you're warm," you know. That's your blood maintaining your core temperature by pumping it around your body like crazy. That's also why if you ever get cold hands, you know, like if you're in a situation where your hands are just freezing, you can do this and just pump your hands a little bit. And what that'll do is that'll draw blood into your hands, and hopefully, you know, that blood is warm in your core and travels out. So that's one of the things that it does. It also removes excess heat through sweat, and it monitors your pH levels and your water equilibrium. So, you know, you need to make sure that you have water distributed pretty evenly throughout your whole body, because water is making it easier for hydrolysis to happen. And it also makes it easier for nutrients to travel. So we definitely want to be able to monitor our water levels. Your blood is responsible for that. When you are dehydrated, you know, a lot of people think it's like, I'm a little dehydrated right now, you know, and it's not really that big a deal. I still got plenty of energy. I'm up and I'm walking around. You got to remember, your blood is actually thicker. So like other things happen when you're dehydrated. It's not just like, you know, you're a little parched. It's not just that you're a little thirsty. Like when you are dehydrated, your cells are having a harder time producing energy. You are having a harder time moving nutrients around your body, and your blood is thick. It's really thick. It's like, you know, it's stickier. And so like people who are chronically dehydrated, you know, they're at a higher risk for blood clots, and it can increase your blood's pressure because now your heart has to pump harder to get that sludge type blood, you know, moving through your body rather than the nice, you know, fluid version. I walked myself into a corner on that one. And then the other main job, and this is, you know, this is the one that we spend most of our time talking about of your cardiovascular system, is it distributes oxygen and nutrients to the different parts of the body. That's really our main, you know, piece of the conversation today. Its job is to deliver oxygen from your lungs, you know, all the way down to your left big toe, you know, which is about as far away from the heart as you can get. Or I guess your right big toe would be further. And, you know, it's also got to be able to get like glucose from your digestive system up against gravity to your brain. And so that's really what we're looking at. That's your cardiovascular system's entire job. So let's go ahead, and I want to start you guys on a crash course video today. So we're going to talk about the heart here real quick, and then we're going to talk all about how we generate and maintain that pressure. This is a really fun episode. If we ever get to it.
A lot. Your heart, that throbbing, beating muscle, is probably the most iconic organ in your body. No other organ gets its own holiday or as much radio play, and you're unlikely to get a love note decorated with a kidney or a spleen or even a brain, which is really what rules the emotions. Don't get me wrong, the heart does some great things. Namely, it powers the entire circulatory system, transporting nutrients, oxygen, waste, heat, hormones, and immune cells throughout the body over and over. But in the end, the heart does not make you love. It doesn't break apart if you get dumped by your boo. It's not a lonely hunter. The truth is, the heart is really just a pump, a big, wet, muscly brute of a pump. And it doesn't care about poetry or chocolate or why you're crying. The heart has only one concern: maintaining pressure. If you've ever squeezed the trigger on a squirt gun or opened a can of shaken soda, You've seen how fluids flow from areas of high pressure, like inside the gun or the can, to areas of low pressure, like outside. The heart's entire purpose is to maintain that same kind of pressure gradient by generating high hydrostatic pressure to pump blood out of the heart while also creating low pressure to bring it back in. That gradient of force is what we mean when we talk about blood pressure. It's basically a measure of the amount of strain your arteries feel as your heart moves your blood around. More than 5 liters of it at about 60 beats per minute. That's about 100,000 beats a day, 35 million a year, 2 to 3 billion heartbeats in a lifetime. The basic physiology of which you can easily feel just by taking your own pulse. I don't have a watch. Now that might not inspire so much poetry, but it turns out it's still a pretty good story. Let us begin with a little anatomy. Unless you happen to be of the Grinch persuasion, the average adult human heart is about the size of 2 fists clasped together. One of the few bits of trivia you often hear about human anatomy that is actually true. The heart is hollow, vaguely cone-shaped, and weighs only about 250 to 350 grams, a pretty modest size for your body's greatest workhorse. And although Americans tend to put their right hand over their left breast while pledging allegiance, the heart is actually situated pretty much in the center of your chest, snuggled in the mediastinum cavity between your lungs. It sits at an angle, though, with one end pointing inferiorly toward the left hip and the other toward the right shoulder, so most of its mass rests just a little bit left of the mid-sternal line. The heart is nestled in a double-walled sac called the pericardium. The tough outer layer, or fibrous pericardium, is made of dense connective tissue and helps protect the heart while anchoring it to some of the surrounding structures, so it doesn't let it bounce all over the place while it's beating. Meanwhile, the inner serous pericardium consists of an inner visceral layer, or epicardium, which is actually part of the heart wall, and an outer parietal layer. These two layers are separated by a thick film of fluid that acts like a natural lubricant, providing a slippery environment for the heart to move around in so it doesn't create friction as it beats. The wall of the heart itself is made of yet more layers, 3 of them. That epicardium on the outside, the myocardium in the middle, which is mainly composed of cardiac muscle tissue that does all the work of contracting, and the innermost endocardium, a thin white layer of squamous epithelial tissue. Deeper inside, the heart has a whole lot of moving pieces that I'm not going to pick apart here, because the really big thing to understand is how the general system of chambers and valves and veins and arteries all work together to circulate blood around the body. Of course, fluid likes to move from areas of high pressure to areas of low pressure, and the heart creates those pressures. Form, once again, following function. Your heart is divided laterally into 2 sides by a thin inner partition called the septum. This division creates 4 chambers, 2 superior atria, which are the low pressure areas, and 2 inferior ventricles that produce the high pressures. Each chamber has a corresponding valve, which acts like a bouncer at a club at closing time, like he'll let you out, but not back in. When a valve opens, blood flows in one direction into the next chamber, and when it closes, that's it. No blood can just flow back into the chamber it just left. So if you put your ear against someone's chest, and yeah, ask for permission first, you'll hear that lub-dub. Lub-dub. What you're really hearing are the person's heart valves opening and closing. It's a relatively simple but quite elegant setup, really. Functionally, those atria are the receiving chambers for the blood coming back to the heart after circulating through the body. The ventricles, meanwhile, are the discharging chambers that push the blood back out of the heart. As a result, the atria are pretty thin-walled because the blood flows back into the heart under low pressure, and all those atria have to do is push it down into the relaxed ventricles, which doesn't take a whole lot of effort. The ventricles are beastly by comparison. They're the true pumps of the heart, and they need big, strong walls to shoot blood back out of the heart with every contraction. And the whole thing is connected to the rest of your circulatory system by way of arteries and veins. We'll go into a whole lot more detail about these later, but the thing to remember first, if you don't already remember it, is that arteries carry blood away from the heart, and veins carry it back toward the heart. To differentiate the two, anatomy diagrams typically depict arteries in red while veins are drawn in blue, which incidentally is part of what has led to the common misconception that your blood is actually blue at some point, but it isn't. It is always red. It's just a brighter red when there's oxygen in it. So let's look at how all this comes together, starting with a big burst of blood flowing out of your heart. The right ventricle pumps blood through the pulmonary semilunar valve into the pulmonary trunk, which is just a big vessel that splits to form the left and right pulmonary arteries. From there, and this is the only time in your body where deoxygenated blood goes through an artery, the blood goes straight through the pulmonary artery into the lungs where it can pick up oxygen. It finds its way into very small, thin-walled capillaries, which allow materials to move in and out of the bloodstream. In the case of the lungs, oxygen moves in and carbon dioxide moves out. The blood then circles back to the heart by way of 4 pulmonary veins, where it keeps moving to the area of lowest pressure, because that is what fluids do. And in this this case, that's the inside of the relaxed left atrium. Then the atrium contracts, which increases the pressure so the blood passes down through the mitral valve into the left ventricle. So the thing that just happened here, where a wave of blood was pumped from the right ventricle to the lungs and then followed the lowest pressure back to the left atrium, there's a name for that. It is the pulmonary circulation loop. It's how your blood unloads its burden of carbon dioxide into the lungs and trades it in for a batch of fresh oxygen. It's short, it's simple, at least in the way I have time to describe it, and it's just delightfully effective. Of all the substances you need to continue existing, oxygen is the most urgent, the one without which you will die in minutes instead of hours or days or weeks. But it's pretty useless unless the oxygen can actually reach your cells, and that hasn't happened yet. For that, your newly oxygenated blood needs to travel through the rest of your organ systems and share the wealth. And that fantastic journey, known as the systemic loop, begins in the left ventricle when it flexes to increase pressure. Now, the blood would like to flow into the nice low-pressure left atrium where it just came from, but the mitral valve slams shut, forcing it through the aortic semilunar valve into your body's largest artery, nearly as big around as a garden hose, the aorta, which sends it to the rest of your body. And after all your various greedy muscles and neurons and organs and the heart itself have had their oxygen feast at the capillary bed buffet, that now oxygen-poor blood loops back to the heart, entering through the big superior and inferior vena cava veins straight into the right atrium. And when the right atrium contracts, the blood passes through the tricuspid valve into the relaxed right ventricle and right back to where we started. This whole double loop cycle plays out like a giant figure eight, heart to lung to heart to body to heart again, and runs off that constant high pressure, low pressure gradient exchange regulated by the heart valves. So the first lub that you hear in that lub-dub is made by the mitral and tricuspid valves closing. And they do that because your ventricles contract to build up pressure and pump blood out of the heart. This high pressure caused by ventricular contraction is called systole. Now, the dub sound. And just to be clear, I'm not talking about dubstep sounds. That's the aortic and pulmonary semilunar valves closing at the start of diastole. That's when the ventricles relax to receive the next volume of blood from the atria. When those valves close, the high pressure blood that's leaving the heart tries to rush back in, but runs into the valves. So you know when you get your blood pressure measured and the nurse gives you two numbers, like 120/80. The first number is your systolic blood pressure, essentially the peak pressure produced by the contracting ventricles that push blood out to all of your tissues. The second reading is your diastolic blood pressure, which is the pressure in your arteries when the ventricles are relaxed. These two numbers give your nurse a sense of how your arteries and ventricles are doing when they're experiencing both high pressure, the systolic, and low pressure, the diastolic. So if your systolic blood pressure is too low, that could mean that, say, the volume of your blood is too low, like maybe you've lost a lot of blood or you're dehydrated. And if your diastolic is too high, that could mean that your blood pressure is high even when it's supposed to be lower. Considering how much we've talked about the importance of homeostasis, it should come as no surprise that blood pressure that's too high or too low, or anything that affects your blood's ability to move oxygen around, can be dangerous. Prolonged high blood pressure can damage arterial walls, mess with your circulation, and ultimately endanger your heart, your lungs, brain, kidneys, and nearly every part of you. So I guess you could say that the best way to break a heart is to mess with its pressure. But good luck trying to write a song about that. Today you learned how the heart's ventricles, atria, and valves create a pump that maintains both high and low pressure to circulate blood from the heart to the body through your arteries and bring it back to the heart through your veins. We also talked about what systolic and diastolic blood pressure are and how they're measured. Thanks to our headmaster of learning, Thomas Frank, and to all of our Patreon patrons who help make Crash Course possible for free through their monthly contributions. If you like Crash Course and you want to help us keep making these videos and also maybe want to get some cool stuff, you can check out patreon.com/Crash Course. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yale, edited by Blake T. Bastino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins. The script supervisor and editor is Nicole Sweeney. Our sound designer is Michael Aranda, and the graphics team is Thought Cafe.
Okay. So, all right, so that is a very speedy but very accurate overview of sort of like what we're going to talk about when we talk about the heart here, right? Like it is all about those chambers and how our body is going to use those chambers to generate but also maintain all of the pressure, right? And luckily your heart's really, really good at contracting in order to be able to do that. So, when we're looking at our heart chambers here, actually, where do I want to be? Right there. So if we define the heart all by itself, right? Actually, hold on. It drives me crazy when I can't get it perfectly on the line. Yeah, there we go. Oh, God, I had it. There we go. So the heart. Your heart is a muscular blood pumping organ that is responsible for generating and maintaining pressure, like we said, right? It is enclosed in this little sac that is called your pericardium. Like if you look at your heart, you will see this little sac that sort of surrounds it and holds it in place. That's actually a really good picture of it right there, because you can really see it's really thick looking in that picture. It's not quite that thick looking. Actually, there we go. That's actually a really good one. So you can kind of see, right? This pericardium is responsible for acting as like connective tissue to keep your heart lodged where it's supposed to be. It's going to keep your heart in the dead center of your chest cavity there, right? And it's responsible for also making sure that it's really slick on the inside, so that like when your heart beats, it's not ever going to get stuck to the walls of that empty sac. So that's your pericardium, right? And peri, it means it's around the, and you know, we're going to get the word cardium from the word that obviously means heart, but peri is coming from the prefix that means perimeter, right? So, you know, it's surrounding the perimeter, holding your heart in place in the same way that, like, you know, if you're trying to keep your dog in the yard and you create, like, you're trying to create a perimeter. Anybody else's dogs run off? Ours do. So then on the inside of your heart, you've got these four main chambers, right? And so those four chambers are going to either be your atriums, which we actually refer, the plural is actually atria, but you've got your left atrium and your right atrium, or it's going to be your left ventricle or your right ventricle. So you've got atria and you've got ventricles. And atrias are all about like gathering blood. Like if I actually even look at the word like atrium, I should find a picture, you know, just Google in the word atrium. Yeah, you can see like it's this big meeting place. You know, it's this big empty chamber that allows you to kind of like meet before going to wherever it is you're going, you know. Like you'd start in here and then, you know, walk wherever. So that's actually like very similar to how atriums are in your heart as well, right? They're these big empty chambers, and it's where blood gets poured back into the heart, whether it's coming from the lungs or if it's coming from like the rest of the body. And then you've got your ventricles, and your ventricles are the really muscular part of your heart. That's what's pumping blood out of your heart to get it to either the lungs or the rest of the body. So those are what we see in our atriums versus ventricles. And we'll go ahead and look at these a little bit more in depth here. Hold on just a second. I'm going to skip forward for just a second. Okay. They're really not spending a lot of time on the chambers here, but knowing these chambers is actually kind of a big part. This is another example of, you know, one thing I actually haven't talked about yet. So, you know, my job is to teach you guys anatomy and physiology and get you prepared to be personal trainers and stuff. But it is also to prepare you for how to pass a test, you know? And I want to tell you guys a little bit of a dirty secret in the world of education. Sometimes things that make really good test questions are the same things that will never come up in your jobs. This is actually, I don't know if you guys heard me yesterday say this, but I really didn't like history for a long time. I never really liked taking history class. It was my least favorite subject in school. Not that I don't think it's fascinating now. And I always thought it was kind of cool, these big stories, you know, because I like stories a lot. I'm a huge nerd when it comes to like, you know, consuming movies and books and TV and stuff. So I like really cool stories, but you know, every history class I ever took was like, what year did this happen? You know, and it's like you had to memorize all these dates, and I really never really cared for it. And so, you know, the reason you get asked questions like that in history class, like what year did this happen, is because it makes a really easy to write test question. And it's really easy to give you an A, B, C, and D multiple choice answer. And unfortunately, that is also true in the world of personal training. Is it going to be, you know, are you going to do things that are, you know, in the gym that particularly affect your right atrium versus your left ventricle? No, you're never going to, like, you know, you're going to train the heart as a whole. That's your job, right? But that being said, test questions about heart chambers make really easy to write test questions. And it's really easy to tell if someone has studied the heart or not based on those questions. So this is where I always get a little bit torn up as an instructor, because like I want you guys to be, great trainers, and I want you to, only fill your brain with the knowledge that's going to help you in your careers. But at the same time, I've also got to fill your brain up with some things that are going to make you a good test taker. One of those things is making sure that you memorize the different chambers of your heart. So making sure that you know the left versus the right versus the left versus the right here, and knowing what atriums versus ventricles are, and knowing what direction they're pumping and what it is that they're doing, that is a big part of the test taking process. So, it's almost like I want to apologize on behalf of kind of educators everywhere. I think it's just one of those things. You're going to get a lot of questions, and guess what? Your clients are never going to ask you what the left atrium is, but you need to know it so that you can pass your test. So, all right, I'm done with my little rant here. But let's go ahead and talk about these chambers, okay? So let's look at the heart. I'm going to pull up a picture of, why did I move over here? I'm going to pull up a picture of the heart here. Heart chambers, images. Let me find a good one that I like. Is there one with the lungs on the sides? No, that's a scary picture.
And the top was one.
What's that?
And the top of the, this is what I was telling you. This is good one, I think.
Yeah, oh, you know what? I think actually, I like all of these, but I think I'm going to go with this one that's got the arrows.
Because have more descriptions of
what the valves are and stuff. Yeah. Luckily, you're never going to be tested on the valves, so that's handy. But you will get tested on the chambers. You know what? Actually, I don't like that one because it's not colored. There we go. Let's go with this one. All right. There we go. I love it. Okay. So here's a picture of our heart, right? I'm going to pull this up next to here. All right, so when we're looking at our heart, right, you can see here, there's a lot of different chambers. There's 4 primary chambers, right? The upper chambers, this is your right atrium, and this is your left atrium. And by the way, don't fall for this. This is one of the first topics that I also studied in school. I don't know if I was absent. I don't know if I wasn't paying attention. I don't know like what happened, but literally for the first couple of weeks of me going to school, studying the heart and stuff, I was very confused because I was like, I think my book might be wrong. This is on the left and this is on the right. Yeah, that was 18-year-old me was a big dummy. It is from the anatomic position, which means like it is facing you. If this person was facing you, this would be the right side of their heart, and this would be the left side of their heart, right? So you got to make sure you keep your chambers straight there. So like I said, there are 4 chambers here, and you've got your atriums on top. Atriums, like I said, they are gathering sites. So this is where your heart is gathering blood that has returned, from wherever it was at. Right, so you can see this blue deoxygenated blood, right? And it's got 2 little valves that actually dump the blood into that. That's your superior, what's called your vena cava, and your inferior vena cava. You're not going to see those terms again, but that's what those 2 little chambers are called. And so the inferior vena cava is basically dumping blood back into the heart that's returning from the lower body, and the superior vena cava is dumping blood back into the heart that is returning from the upper body in your brain and places like that. And so all of that blood's going to get dumped into this right atrium. So now it's gathered back into the heart, but the right atrium doesn't really generate that much pressure. So what's going to happen is this little valve right here is going to open up, and that's going to allow blood to get dumped into your right ventricle. Again, this is deoxygenated blood. This is blood that's already been used up. So it has dropped off all of its oxygen, and now it's picked up a bunch of CO2. We got to get that CO2 out of our blood so that we can get some more oxygen in it. So it's got to make its way over to the lungs. So that's what's going to happen right here in the right ventricle. That blood's going to drop into the right ventricle, and then that valve is going to slam shut. So the blood can't travel back here because this is an area of low pressure. So blood wants to go here, and that's why we got the valves. And then what's going to happen is your heart's going to squeeze. And when that happens, blood is going to be ejected from this right ventricle into this tube right here. And that is going to split in two different directions. See how it travels back behind these chambers here, right? Not chambers, these vessels right here. So it's going to travel, half of the blood's going to go this way, the other half of the blood is going to go this way. And that's going to go to either sides of your lungs. Now, your lungs are not really all that far away. So you'll notice this is fairly muscular, but we're about to see a lot more muscle on this side over here. And so that's going to pump blood into your lungs. Now, just like we talked about yesterday, your blood is going to do its job. It's going to drop off all of that CO2, and it's going to pick up all kinds of oxygen. So now you've got bright red blood. Right now it's like really oxygenated blood. It's got tons of oxygen in it. It's got hardly any CO2. It is ready to deliver, right? So now that blood is going to get sucked into this area of low pressure right here. There's very little pressure in your left atrium. So blood's going to get sucked back to the heart. It's going to actually, again, you can kind of see it's passing behind this big arch right here and then this tube right here. So it passes behind that and goes in here. And then, you know, right over here, it's traveling this way. So all that blood's going to end up in your left atrium, which, you know, this valve is closed at first. And then it fills up and the valve opens up, and all that blood's going to rush to this area of low pressure down here. And then that valve is going to slam shut. Your heart's going to squeeze. That creates high pressure, but because that valve is closed, it can only go this way. And the blood is going to get pumped up this little loop right here. Some of it's going to go up to your brain, but the rest of it's going to drop down behind that loop, and it's going to drop behind the heart, and it's going to go out to the rest of your entire body. So this left ventricle right here is kind of the star of the show. This is really our main character when we talk about like the heart, right? Like this left ventricle is actually, whenever it beats, that's what you are sensing when you are like measuring your pulse. You are feeling every time your left ventricle is ejecting blood throughout your body. So when you do like your radial pulse here or your carotid pulse right here, right? I've got an artery, my carotid artery, that's traveling up to my brain. When my heart squeezes, that left ventricle is pumping blood up against gravity, right? And so, you know, this chamber has to pump blood against gravity. It's got to be able to pump blood all the way from my heart down to, like I said, my right pinky toe, which is very far away, right? So this is the very muscular part of your heart, right? This part of your heart right here is extremely muscular. It is responsible for, you know, pumping blood across a really long distance. And so, like I said, this is really what we're measuring right here when we're measuring your pulse. And so what'll happen is that red blood cell is going to, you know, deliver its oxygen. And let's say it is going to my left pinky toe and I'm in the middle of a run, right? I don't know how much work my left pinky toe is doing a run, but it is going to drop off its oxygen that it picked up earlier. It's going to pick up some CO2. And now it's got to get back to my lungs to be able to drop that off. And so, and exchange that CO2 for oxygen. So now, guess what? It's going to travel up through that inferior vena cava, get dumped into the right atrium, where it will flow into the right ventricle. The heart will pump. That will push that blood out into my lungs. It will then get sucked from my lungs back to my heart into the left atrium, drop into the left ventricle, and the left ventricle, you know, and the heart will squeeze again and pump that blood out of my heart. And so that will continue over and over again from before you were born till after you're gone. You know, that, well, until exactly you're gone, I guess. And so that is, you know, it's going from body to heart to lungs to body to heart to lung. Wait, I think I missed one. Heart to lungs to heart to body to heart to lungs to heart to body, right? So continually over and over and over and over again. That is how our heart is traveling. What's up, Noel? We're an hour in. How are you?
All right.
Yeah, good to see you.
Cut, man.
All right, man. We got to figure out how to get you in here at the start of class. That's 3 days in a row.
We're going to figure something out.
So let's keep moving. So those are all of the different chambers of the heart, right? We've got the left atrium. Again, and this is divided into atriums versus ventricles here. We've got the left atrium, which is gathering oxygenated blood, because the left atrium is attached to the left ventricle. And the left ventricle pumps blood out of the heart. So the left atrium gathers oxygenated blood that has returned from the lungs. The right atrium is gathering deoxygenated blood that has returned from the body, right? And then the left atrium connects to the left ventricle, which will push oxygenated blood out of the heart so that it can be delivered to the body. And the right ventricle will push deoxygenated blood to the lungs so that it can pick up new oxygen and drop off its CO2. So, we kind of described it in two different ways there, right? We went like right, left, or you could always do like atrium, ventricle, whichever version of that helps you memorize these chambers the best. That's going to work for you. Everybody's a little bit different. I like to go, I actually don't really, this is not my favorite order. I like to go, I like to start with like a red blood cell that's already done its job, because technically that's actually, this is almost like a what came first, the chicken or the egg, like, because it's a continuous loop, right? So it's like, how do you describe what happened first? Well, technically a brand new red blood cell, when it was born in your bones, so it was created in your bone marrow, right? So the very first time it ever gets to like travel through the heart, it will go through the right atrium into the right ventricle, and it'll make its way to the lungs for the very first time, pick up its oxygen that it's never done before, travel back to the left atrium, then to the left ventricle, and it will do its very first delivery. So that's the order that I like to memorize it in. But if you prefer to do like, all right, my left atrium gathers stuff coming back from the lungs, and my right atrium gathers stuff back from the body, and then just drop it down this way and be like, so that means that, left is going to, go towards the body, and right is going to go towards the lungs. Whichever version of that helps you memorize, more power to you. I think that both are effective. How's everybody feeling so far about those chambers and those directions? Everybody feeling good? Any questions on that?
It's
Is it like in the NASM test?
This is in your, yeah. So yeah, probably. I'm wondering if they'll have the directions in there, but they probably would. We can actually check really quick. Let's find out. We'll go to the NASM blueprint real quick. So remember, this is something you guys are going to get in capstone. This is your exam blueprint. Let's take a look here. So if we go to domain 1, right, 17, you're going to get 17 questions from basic science plus nutrition together. And so, we know that like we need to know all of these systems here. Let's see here, heart. Well, I got to spell it right, heart. Those are assessments, no. This is kind of the short version. Where's the other one? Study guide. There's another one that they put out that will also give you guys this one right here. Muscles, nervous system. Okay, yeah. So in your cardiovascular system, they will want you to know the difference. Yeah, they'll want you to know what atriums are, and they'll want you to know what ventricles are. And they'll want you to know arteries and veins. So you may get a question that says, blood that is returning from the body will drop into the blank atrium, right? Well, if it's returning from the body, it's used up its oxygen, right? So it's going to go into the right atrium so that it can get to the lungs. So yeah, Charlie, you might get a question related to this. So like I said, this is the kind of stuff that it just makes good test questions. And so you sometimes have to prepare for the I really don't like memorization. I think you guys know that. But this is the situation where, memorizing comes in handy. Soraya, what were you saying? You had a comment as well.
What is it?
You had a question or how are you feeling about all this?
Oh, it is too much information, too much things around of the for I know for each part of the organs of the body. It is so much things, and I'm confusing what I need to pick to learn about the concept of the definition and what you suggest me to do with it.
Well, I mean, practice is going to be key, but you're not going to get it all. You might not get it all today, but you'll get it by the time I'm done with you. Remember, I got 9 months with you.
Okay.
So, if you're not an expert today, that's okay. But one of the things that kind of helps me, and I can't draw a heart to save my life. So instead of trying to draw a heart, I will cheat, and we will use Microsoft Paint here. You actually can use Valentine's hearts. They don't actually work that poorly. These are sometimes pretty effective. But what we're going to do here, we'll draw ourselves a little heart, and this is what helped me when I was in school. So remember, it's on the left side because it's facing us. This is the anatomic position. So let's draw ourselves a right atrium, and we've got a right ventricle here. And then we can draw a left atrium, and we can draw ourselves a left ventricle here.
So the heart pumps in the dirty blood and cleans it to clean blood, right?
It doesn't
Clean blood, right?
clean it. I wouldn't. Yeah, I would stay away from that version. So your heart's job is to gather any of the used up blood that has dropped off its oxygen so that it can get it to the lungs. And the lungs are going to exchange things.
Oh, okay.
Yeah. In terms of like dirty versus clean, your liver is going to detoxify your blood. Your liver scrubs it for any toxins and stuff like that. Because your liver is full of all kinds of different enzymes. And those enzymes are what's going to kill any stuff that's, I guess, quote unquote dirty. But in terms of like whether it has oxygen in it or doesn't have oxygen, that's what your heart's job is. Your heart is just a pump. It doesn't have any ability to clean anything. It doesn't have any ability to give it oxygen. It's just getting the blood to where it needs to go. If your blood's dirty, it needs to get it to your liver. If your blood is deoxygenated, it needs to get it to your lungs. If your blood is oxygenated, it needs to get it to your brain and your muscles and your bones, Does that make sense?
Yeah.
So let's draw some arrows here. So we're going to say, we're going to type, so deoxygenated blood. Oop, hold on a second. I want to pick a better font. And I can, if this actually, let's go like that and make it, so deoxygenated. So deoxygenated blood is going to be blood that is returning from the body, right? This is blood that has, dropped off its, it's going to drop off. It's already dropped off its oxygen. So now it needs to get into this chamber right here. Okay. And then what's going to happen is and this is we'll label this here. This is your right atrium. Okay, so that's your right atrium right here. Actually, you know what? I can put this, I'll put this inside. This is the right atrium. That works. And then here we have our right ventricle, left atrium.
Left atrium, left ventricle.
Left ventricle. And what I always tell people, actually, Soraya and everybody else, guys, if you have trouble memorizing this stuff, memorize this one right here. Start with this. If you memorize the left ventricle first, the rest of it you'll remember. All you have to do is, it's like a little logic game. You have to flip everything around, right? What's the opposite of a ventricle? An atrium. What's the opposite of left? Right. So if you start with this, remember what it does, you can remember the other ones. Oh, hey guys, don't forget to to keep that on mute. All right, so the right blood, deoxygenated blood, is going to return from the body, and then it's going to go into the right atrium, and then it will go into our right ventricle. Right. And then what's going to happen is it is going to then pump out to the lungs, and it's going to go kind of like this. Right, so we'll say to the lungs, right, and this is the lungs, and right, so that's pumping out to the lungs, and now you've got oxygenated blood, and so we'll put that down here, so we'll say oxygenated blood, which is returning from the lungs, right? So that is now going to go this way, and it's going to drop in almost the same direction, but it's going to go right in here. Yep. And then again, and I probably should have put this up top, but it's okay. We'll say oxygenated blood returning from the lungs, right? And the same thing is going to happen here. Hey. So that is also going to go here, right? Because we got two sides of our lungs, right? And then it's going to drop into the left ventricle. Right. And then it is going to get pumped out. Whoops, terrible arrow. It's going to get pumped out, and we'll label this to the body. Right. So that's how that's going to work, right? It's going to go from so now it's going to go to the body. Well, guess what? It's going to come right back. Now that it drops off all of its oxygen, it becomes deoxygenated, and it's going to go back into the right atrium, into the right ventricle, out to the lungs, back into the left atrium, back into the left ventricle, out to the body, back into the right atrium, right? We'll draw this one in. We'll draw this. Wait, purple. We'll use purple. I was like, what am I? How I can draw? You know, we'll say this is the purple, and it's going to connect, you know, right there, right? That's the transitionary color. I don't know if that's actually helpful, but that's how that's going to work. So if you guys want to do this, I really do recommend draw yourself Valentine's hearts, unless anybody out there is actually a talented drawer. Artist.
Yeah, but now what we do is, well, for me, it is easy to understand more than the anatomic things.
The weird heart, yeah, the anatomic heart, yeah. Honestly, it's so funny. You know, we're on Zoom right now, but you know, I used to have a giant whiteboard. I used to have a whiteboard that was the size of my entire wall. It was literally the best one in all of Sochi. And I would always they'd always try to move me from one classroom to another, and I'd be like, absolutely, nope, I'm not moving. I got the best way. So this big ass whiteboard, and and I would use it. I would draw my little drawings, and I cannot. So I would draw Valentine's hearts, and it's so funny because Mo is the other PFT instructor. He is an incredible artist. And he would come into my room, and he would be like, I like your Valentine's hearts. And I was like, you don't, but I see what you're doing. So everybody, once you get to capstone, you'll probably see Mo's drawings are much better than mine. But draw yourself some Valentine's hearts. They still work. You can just put the little chambers in them. So that is how the chambers of the heart work. Hopefully that kind of cleared it up for you guys. You got to see it happen slowly in real time. Like I said, if you're going to memorize one, I would memorize this one right here. I'll put it in italics for you. Remember the left ventricle. The left ventricle pumps blood to the body, right? If it's going to the body, it has to have oxygen. So then, if you remember that, you can flip the rest of it around. You're like, okay, the left ventricle pumps to the body, the right ventricle pumps to the lungs, right? So now you just use your, you flip it around, you reverse logic, right? And then, opposite of a ventricle is an atrium. So if the ventricle pumps, the atrium receives, right? So then you go left ventricle, go into the body, right? It's receiving blood. If it's going to the body, it must be oxygenated. It's receiving blood from the lungs. So you can kind of like work yourself around and just reverse engineer your answers. Memorize this one first. If you forget everything that I tell you today, memorize this, okay? All right, let's look at the layers of your heart, because here's where we get a little bit into our conversation on muscles, right? So muscles, which, is what a lot of you guys are here to talk about, right? Let's go ahead and take a look at the muscles of the heart. Your heart is this really muscular organ, and it's got several different layers in it. And actually, let me show you the different layers of your heart here. So we go layers of the heart, layers of the hair. I can never type heart. What is wrong with me? So your heart actually looks like this. This is actually what the walls of your heart look like. Remember that layer that I told you about earlier, that pericardium, right? This is that little fibrous sac right there. So there's that little fibrous sac around the outside of your heart. And then actually, here's a really good picture as well. You can see there's an innermost layer that's really, really smooth from that pericardium that is keeping the heart from getting stuck to it. It's got a whole bunch of basically like this mucus that keeps it really nice and slick. And then you've got the outermost layer of the heart's tissue itself. And that outer layer is going to protect separating the heart from that little fibrous sac that holds it together. And so there's your outermost layer, right? And then look at this really thick layer right here. Look at how wide and thick that layer is, right? Look at all this. See all that muscle, right? It's a little thinner out here, but look at how muscular this part of your heart is, right? Well, that is your myocardium. And remember, myo comes from the word muscle. Cardium comes from the word that means heart. So it is your heart muscle. This is the most muscular layer of the heart. It's extremely thick compared to the other layers because that is where contraction is taking place. Your heart's ability to squeeze itself is because of your myocardium. And if you look at it, look at the design here, you'll notice, see how this side's kind of thin? Remember, this is your right ventricle. It's only got to pump blood over to the lungs. It doesn't have to make that strong of a contraction. It's a couple inches away, right? But this layer, look at how freaking thick and, wide this layer is. That's your left ventricle. Your left ventricle has got to pump blood against gravity up to your brain. It's got to pump blood all the way down to your feet. If you were standing on your hands, it's still got to pump blood to your feet against gravity. Like, this is an extremely muscular part of your heart that's really designed to push pretty far away. So we get the thinner layer over here and the thicker layer over here. And so those are most of the layers. And then we got one final layer, which is kind of hard to see in that picture. So we'll pull up a different one here. See this really, really, really thin layer right here. So there's the myocardium. This really thin inner layer, that's your endocardium. Endo comes from the word that means inner. And your endocardium is the inner, like the chambers of your heart, right? It's the inner part of it. In the same way that if you were to grab some of your skin, you've got your outer layers, which are really tough because, you gotta be able to bang it on stuff and hopefully not get a cut. That's your outer layers. But your inner layers on the inside of your skin, they're really soft and smooth because we don't want those layers to have friction against any of the materials inside our body. Same thing is true in your heart. Your innermost layer is super smooth. In fact, there's actually a disease called endocarditis, which is where the inner chambers of the heart, due to like high pressure or maybe some materials that shouldn't have gone through the heart, actually mess up that inner layer. And that's really dangerous because if it gets any type of texture, if it's not really smooth, red blood cells can start clotting in the heart. And then that can cause congestive heart failure and all kinds of other things. Pretty freaking rare, but you know, it can still happen. So your epicardium is the outermost layer, right? Like the epicenter of something. It's around the outside. Your myocardium is the middle layer, and it's extremely muscular. Myo for muscle, cardium for heart muscle. And then your endocardium, endo means inner, and cardium is those are the inner layers of your heart. So those are your three main layers. It isn't listed here. I think I got it up here somewhere. Yeah, there's also one final extra layer, which isn't really part of your heart, but your pericardium. And the pericardium is that sac that I mentioned earlier, around the perimeter, holding your heart in your chest. Anybody ever heard, oh God, actually, I can't remember the name of it. Marfan's. Anybody ever heard of Marfan's syndrome? Anybody
No,
ever heard?
what is it?
Yeah, so I got to remember how to spell it. I think it's Marfan's syndrome. Yeah. I can spell stuff. So Marfan's syndrome is actually a condition. Let me see if I can find an image here. Yeah, so here's a really famous story. So I don't know if you guys remember this, but there was this this college basketball player right here. And you kind of look at him and you see he's extremely long. He's extremely thin. And so Marfan's syndrome is something that they don't necessarily always pick up on when you're in college, but the NBA will actually test for it. And if you have it, unfortunately, they don't allow you to play in the NBA. Here's another example. You can see here. Sometimes you'll see it look like you'll see these little dents or you'll see these little protrusions in the chest. And what Marfan syndrome is, it's a genetic condition where your connective tissue is actually a little elongated compared to the average person. Your connective tissue is a little weaker than the average person. And the reason they don't let people in the NBA have this is because it's a semi-contact sport. So if you have weak connective tissue and you get hit really hard, something might not stay connected. It might, come dislodged. So Isaiah Austin was this pretty, really, really, really great, college basketball player. And he was going to be in the NBA. He was going to get drafted because he was really, really good. And unfortunately, it turns out that he had Marfan syndrome, which is probably what led to him being so tall and long. And so the NBA couldn't let him in, but it was a really cool ceremony. They brought him to the draft. And I think he got drafted by New Orleans. I'm not 100% certain on that. Don't quote me on that last part, but he got drafted and then they let him retire instantly. But it was a really nice thing that the NBA did. They drafted him, so he made it into the NBA, but he never obviously got to play.
Ain't that's where the skin forms around the heart and it don't have that shield around it?
Close. That I like your understanding. Yeah, it's not quite where it doesn't have like a shield. It's where your pericardium, which is that fibrous sac that holds your heart in place, doesn't, it's weaker. So if you get hit really hard in the chest, your heart could literally fall off, which means that it would become, dislodged. That's why it's so dangerous. I mean, it's not like it's gonna, it's not like they have to worry about bumping into somebody at the supermarket. It's not that severe, but the NBA, you can take a hard hit every now and then. So that's the reason they don't let people with that condition play.
Don't they got to wear some type of shield or something on their chest or something?
Yeah, you'll see stuff like that sometimes. You'll see some things like that. I can't speak to whether or not that actually helps. I don't know. At that point, I stopped knowing enough. We reached the end of my knowledge. So anyway, that's your pericardium. And it's not listed here in the main layers of the heart because technically it's connective tissue around the heart. All right. So now we got to talk a little bit about like how your heart is actually going to create electric signals, right? Let's talk about how your heart actually generates electricity. So your heart generates its own electric signals. And I want to show you a quick little video that's going to kind of explain that. We got one more crash course video today. Crash course heart part 2. All right. So now we're going to move into the conversation. This is also going to get into our conversation on blood. This is going to pivot into our conversation on blood vessels as well. So we're going to talk about the heart's electric signals, but we're also going to talk about like the pressure that your heart generates. So we are going to get into the idea of blood pressure here.
You've seen this before in a TV show or a movie. A patient is on the table in the emergency room, bleeding from a stab wound or having OD'd on drugs, when suddenly an alarm goes off and the beep, beep, beep of the heart monitor flatlines. It's cardiac arrest, and you can tell just by that sound that it's terrible. Doctors swarm around barking orders, and McDreamy or Dr. Gray or whoever the latest foxy doctor is on the TV show that you're addicted to grabs the paddles and pushes them down on the patient's chest and is all, clear! Then the patient's chest jumps up, and everyone stares at the monitor waiting for those steady beeps to reappear. That is a pretty classic scene. When it comes to medical crises you see in popular culture, it's probably only rivaled by the poolside CPR scene or someone shaking an unconscious body, pounding on their chest and saying, "Don't you die on me," which hopefully you know is no way to keep someone alive. These are classic script tropes, but they contribute to some misconceptions about how defibrillators, CPR, and the electricity of the heart work. Because the truth is, CPR can help prolong heart function during cardiac arrest, but it usually can't save a life without help from a defibrillator. And when McDreamy, may he rest in peace, finally bursts out those paddles, that high voltage shock isn't turning the heart back on, it's actually stopping it. Confused? Well, I'm here to get your head to understand your heart. We'll get back to hot TV doctors in a couple of minutes, I promise. But in order to understand what's actually going on during cardiac arrest, we have to understand some basics about your heart cells. We've learned a lot about skeletal muscle tissue, how it's striated and contracts using the actin-myosin sliding filament dance you've heard so much about. Your cardiac muscle is also striated and uses sliding filaments to contract, but the similarities end there. For one, their cells look pretty different. Skeletal muscle tissue has long multinucleate cells, while cardiac cells are squat, branched out, and interconnected, each one with one or two central nuclei. The cells are separated by a loose matrix of connective tissue called the endomysium, which is chock full of capillaries to serve up a constant supply of oxygen. Cardiac cells are also loaded with energy-generating mitochondria. In fact, mitochondria take up as much as 25 to 35% of each cell.
That is crazy, right? Look at how much mitochondria is in your heart cells, way more than you're going to find in most tissues of the body. And that's because, you know, we really don't want our heart to stop producing energy and to stop beating. So, you know, when it comes to like the idea of type 1 versus type 2 muscle fibers, this is the most type 1 that you could ever possibly get. But we don't really call it that. We call it cardiac muscle. It gets its own name. And you can see, like I said, it's got one nucleus. That your nucleus is kind of like the brain of your cells. We don't want too many cooks in the kitchen, right? We don't want too many people making decisions. We want one central decision maker. And so lots of mitochondria for energy production, single nucleus, and then it has the ability to contract, and it's covered in capillaries. There are capillaries running like crazy through all of your heart's tissues that allow those tissues to get lots of oxygen so that mitochondria can use that oxygen.
Mitochondria. In fact, mitochondria take up as much as 25 to 35% of each cell, making it resistant to fatigue, which is partly why your heart can beat nearly 3 billion times in a lifetime. Not surprisingly, the differences between skeletal and cardiac muscle tissues are key to understanding their function. Skeletal muscle fibers are both structurally and functionally separate from each other, meaning that some cells can work while others don't. That's why you can grasp a delicate flower with the same hand that you can use to crush a soda can. Cardiac cells, on the other hand, are both physically and electrically connected all of the time. It takes precise coordination to create the high and low pressures required to pump your blood, after all, and cardiac cells need to be linked in order to have that perfect timing. And there's one more thing you need to know about your heart cells. Some of them can generate their own electricity. How in the name of Raymond de Voussons can that be? Well, rewind your brain to when we explored the electrical marvel that is the action potential and how it triggers both neurons and muscle cells. That process started by depolarizing the cell, that is, pushing the cell's membrane potential from negative toward positive past a threshold that triggered voltage-gated ion channels to open. Most cells in your body only depolarize after being triggered by an external stimulus or by a neighboring cell in a long chain reaction of action potentials that's set off by the nervous system. But that is not the case for a special group of cells found only in your heart, ones that can trigger their own depolarization. These are your pacemaker cells. Pacemaker cells are what keep your heart beating at the correct rhythm and ensure that each cardiac muscle cell contracts in coordination with the others, because you don't want your brain to have to send a series of action potentials every time you need your heart to beat. Your brain has got other stuff to do. So pacemaker cells are, in a way, your heart's very own brain, generating the initial spark that sends a current through your heart's internal wiring system, known as the intrinsic cardiac conduction system. This system transmits electricity along a precisely timed pathway that ends with atrial and ventricular contractions, also known as heartbeats. And it begins with pacemaker cells generating their own action potentials. In most cells, the action potential starts with the resting potential, which the cell maintains by pumping sodium ions out and potassium ions in, right? Then, when some stimulus causes the sodium channels to open up, the sodium ions flood back in, which raises the membrane potential until it reaches its threshold. Pacemaker cells operate the same way, except for that initial stimulus. They don't need it. Their membranes are dotted with leaky sodium and potassium channels that don't require any external triggers. Instead, as their channels let sodium ions trickle in, they cause the membrane potential to slowly and inevitably drift toward its threshold. Since the leaking happens at a steady rate, the cells fire off action potentials like clockwork, and the leakier the membrane gets, the faster it triggers action potentials. The pacemaker cells at the start of the conduction system have the leakiest membranes, and therefore the fastest inherent rhythms, so they control the rate of the entire heart. And those fast, leaky cells are found in the sinoatrial node, or the SA node, up in the right atria. They essentially turn the whole SA node into your natural pacemaker. After those pacemaker cells make themselves fire, they spread their electrical impulses to cardiac muscle cells throughout the atria. The impulses leap across synapse-like connections between the cells called gap junctions and continue down the conduction system until they reach the atrioventricular node, or AV node, located just above the tricuspid valve. Now, when the signal hits the AV node, it actually gets delayed for like 1/10 of a second, so the atria can finish contracting before the ventricles contract. Without that delay, all the chambers would squeeze at once, and the blood would just splash around and not go anywhere. So instead, the atria contract and blood drops down into the ventricles, and then a moment later, the signal moves on and triggers the ventricles to squeeze, making the blood flow out of the heart. And there are two tricks to a good ventricular contraction. One, the ventricles are so large that the signal has to be distributed evenly to ensure a coordinated contraction. And two, the ventricles need to squeeze like they're squeezing a tube of toothpaste from the bottom up to accelerate the blood through the big arteries at the top of the heart. So from the AV node, the signal travels straight down to the inferior end of the heart and gets distributed to both sides. The path the electrical impulse takes to the bottom of the heart is called the atrioventricular bundle, also known by the more rad name, the bundle of His, where it branches out to the left and right ventricles. Finally, the signal disperses out into Purkinje fibers, which trigger depolarization in all surrounding cells, causing the ventricles to contract from the bottom up like toothpaste tubes, at which point the whole cycle starts all over again. And everything I just described to you, from when the SA node fires to when the last of the ventricular cells contract, takes about 220 milliseconds. So that is how your heart beats. But I know what you want. You want to get back to talking about TV shows and McDreamy and his paddles. It's totally understandable. Okay, so picture all your individual heart cells as a bunch of musicians in an orchestra. They all sound really great together, but then the conductor suddenly needs to go to the bathroom. And it sounds okay at first, but then the tuba gets a little weird and the triangles have a beat off, and soon everyone is playing a different note at a different time, jamming to their own personal rhythm. In the heart, we call this out-of-sync behavior fibrillation. And it can be caused by all sorts of problems, especially ones that affect the pacemaker cells in the SA node. In an orchestra, this just sounds really terrible. In a heart, there's no coordinated contraction, no love-dub, no blood moving through the body, which means you will soon be dead. But then the conductor comes back from the bathroom break, taps her wand, and everybody stops. It's silent for a second before the wand comes up, and then they all start playing again, this time in unison. If your heart in fibrillation is an out-of-sync orchestra, then a defibrillator is that conductor. It stops the chaotic noise by overriding all of the individuals and hits a sort of reset button, so everyone can start again on the same page. The paddles send so much electricity through the heart that they trigger action potentials in all of the cells at once. Then the cells repolarize and start leaking again, and the most leaky cells in the pacemaker SA node reach their threshold and fire first, resetting the rhythm that keeps everyone in harmony so your heart functions properly. And that is how hot doctors and their paddles actually stop hearts to save lives. Now, the thing about CPR, or cardiopulmonary resuscitation, is that it can't correct fibrillation. What those chest compressions can do is force a fibrillating heart to keep circulating oxygenated blood until help arrives. But if a person is in cardiac arrest, just breathing into their mouth and compressing their chest won't deliver the electricity needed to give the pacemaking cells a chance to reset. I think I just figured out why they call those TV doctors heartthrobs. Anyway, today you learned how your heart's pacemaker cells use leaky membranes to generate their own action potentials and how the resulting electricity travels through the cardiac conduction pathway from SA node to Purkinje fibers, allowing your heart to contract. And if you weren't too busy daydreaming about TV doctors, you also learned how defibrillators work to reset the rhythm of your heart. Thank you to our headmaster of learning, Thomas Frank, and to all of our Patreon patrons who help make Crash Course possible through their monthly contributions, not just to themselves, but to everyone in the world for free. If you like Crash Course and want to help us keep making these videos, you can visit patreon.com/crashcourse. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. The episode was written by Kathleen Yale, edited by Blake DiFestino, and our consultant is Dr. Brandon Jackson. It was directed by Nicholas Jenkins. The script supervisor and editor is Nicole Sweeney. Our sound designer is Michael Aranda, and the graphics team is Thought Cafe.
Okay, so obviously that was like a lot, right? That one moves really quick. But here's the thing. Your heart cells and every cell in your body, I'm going to open some sort of a new example here. So every part of your body it's separated by these membranes, right? And some of these membranes are, negative on one side and positive on the other side. So there's a difference in electric charge, right? But what will happen is your body will use, if you zoom in on this, right? Like if I zoom in on this little section right here, what we're going to see is there's actually separating. There are sodium ions on one side. So sodium is chemical signal Na, right? And sodium ions are super, super positive, right? I'm sorry. Sodium ions, they're positive. And then you've got potassium ions, which are also positive, but they are less positive. So they are, less positive, and these are more, right? And so what happens is like there's a difference in electric charge. So what that means is that there's a positive signal on this side and a negative signal on this side. And what your body will do is it will push things in one direction and it will flip these. And so then what you're stuck with is you're stuck with this separated, positive here, and then it goes negative, negative, negative. And then you've got negative here, and it's positive, positive, positive. Now, you remember yesterday when I told you, or I actually think this was 2 days ago, nature really hates it when there's a lot of stuff in one place and very little stuff on the other. So nature hates gradients. It's like nails on a chalkboard. So now that this has created a gradient where there's more stuff on one side and less stuff on the other, nature is going to naturally try to move this back in this direction. And when that happens, electrons are passing past each other, and that creates electric charge. That's what happens when, you take your shirt off and you hear all that like static electricity. It's when you rub your feet on carpet and you build up a lot of static electricity. You're basically moving electrons so quickly that there's escaping electric energy. Your cells push those things that generate electric energy back and forth. That is also why, and I don't have one here, but that is also why when you look at like the batteries in a remote, it looks like this, right? You've got a battery here and you've got another battery here, and you keep them, when you put batteries in something, you've got your positive end and your negative end. And the reason you have them reversed from each other is because that creates this like electricity that continually travels like back and forth. And so it's having them opposite like that generates electric charge, right? So your heart cells have these little chambers, these little like channels, these little spaces between them where sodium and potassium ions move back and forth. And that moving back and forth creates electricity, right? It is literally as if your heart is rubbing its feet on carpet, right? I don't know if you guys did that when you were a kid. I used to do it all the time. I used to like walk around and zap stuff because it made me feel like I was like a superhero. So that is exactly what's happening. So where does what's up?
Hey, have you ever watched the movie Crank?
Yeah. Yes, I have. God, that's
when his heart would just be thumping, and he got to keep moving. If he stopped moving, his heart gonna stop. He could die.
Yep. So that actually, that movie is so silly. But yeah, that movie, for those of you who don't know, it's about a guy who I think I think they take his heart out and he gets it put back. Something happens, his heart's dying. And so he has to keep like electrocuting himself through the whole movie to like keep himself alive. And like he injects himself with adrenaline. He does all this like different stuff to keep his heart pumping. And like at one point he grabs a defibrillator and he shocks himself. But yeah, so, what he's doing is he's keeping his heart pumping with like this electricity, right? And so when we look at that, right, inside of your heart is continually generating this electric charge, right? And that's all happening in this main chamber of the heart. Well, this is the chamber I want you to memorize, but it's happening in this chamber right here. This is where you're going to have this thing called your SA node, right? So this is your SA node, and it lives in your right atrium. This is the pacemaker of the heart. Okay, that is a term everybody needs to know. You need to know where it lives. It lives in the right atrium, and you need to know what it does. It sets your heart's rhythm. So the reason it sets your heart's rhythm is because it can generate the electric signal louder than any other cells in the heart. So because it's the loudest, it's the conductor. It's in charge of generating that electric signal. And so it lives, like I said, in that right atrium there. So the pacemaker of the heart responds to chemicals that run throughout the body. So how does it determine whether to speed your heart up and speed your heart, slow your heart down? Well, there's chemistry coming into your heart. If that right chamber receives blood that came back from the heart, like you remember we talked about, like this is all deoxygenated blood, right? Like this is all blood that is returning from the heart. So, if I asked you, like if you were doing like a bunch of squats and now the blood from your quadricep muscles and your glutes, right? That blood got all of its oxygen stripped out of it, and now it's carrying a bunch of CO2. So if this very acidic blood drops into that right chamber, the SA node goes, we're doing work. And it makes your heart beat faster. So it is connected to your nervous system, and it's connected through chemistry. And if the chemistry of your blood changes, it will either speed your heart up or it will slow your heart down. Or if your nervous system decides like, you have no conscious control over your heart rhythm, but you can do certain things that will raise you can't make your heart beat. Like I can't be like, beat, 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 right? I can't do that. But what I can do is I can be like, I can think about something that makes me really scared, or I can think about something that makes me really nervous. And like that will start producing stress hormones. And guess what? If stress hormones run by your SA node is like tasting that. It's like, oh God, adrenaline. We should start beating, right? So if it tastes adrenaline, it will make your heart beat faster. And that's how your SA node controls your heart rhythm. That's your pacemaker of the heart. Responds to chemicals throughout the body, particularly adrenaline, that will speed up and therefore speed up your entire heart. Now, the SA node is connected to what's called your AV node, which is responsible for delaying the signal. That's why, the upper chambers contract before the lower chambers, creating that high and low pressure. And then it will spread out to your Purkinje fibers, which are all the fibers that are running throughout the rest of the heart. I do not think you guys will get questions related to these two, but I promise you will have a question related to the SA node. This is the big one that you want to have memorized. These two are important for, us understanding the rest of the heart signal, but I don't think you're going to get questions related to them. All right, so that is the end of the conversation about the heart. We are going to move on to blood vessels. Does anybody have any questions before we move on?
Yeah, then what about the adrenaline? What does adrenaline do?
So remember, adrenaline is going to run past your SA node, and when your SA node senses adrenaline, it will speed up your heart.
Oh, okay.
So adrenaline is a stress hormone, just like cortisol. Cortisol will also speed up your heart. Any other questions? That was a good one.
I wasn't understand what was the question of him.
Just any questions before we move on? We're gonna.
What the person was asking.
What does adrenaline do? Adrenaline is a hormone that is made by your kidneys, actually, but adrenaline is in charge of amping up body tissues. Somebody figured out how to use the draw feature. You do me a favor and erase that. Otherwise, that's going to be there for the rest of the lecture. I don't know how to get rid of that stuff once it gets drawn on there. We might have a hair on the screen for the rest until somebody figures out how to remove that. So yeah, adrenaline's job is to amp up things inside of your body. If adrenaline runs by your SA node, it will speed up your heart. Yes. Yeah. All right. So let's go ahead and talk about. Thank you. Let's talk about blood vessels. Okay. So blood vessels, these are the tubes that are allowing blood cells to travel throughout your body, right? Like this is the subway system for, blood to travel around to wherever it needs to go. And so you have got three main categories here, and then there's some couple little small ones, but three main categories. You've got arteries, which are carrying blood away from your heart, veins, which are carrying blood towards your heart, and capillaries, which are the meeting place where, it's a big artery, it drops the blood off in the capillaries, and then the capillaries come together to make up eventually they'll become a vein, right? So, again, it's a closed system. Here's how we usually draw this. If we look at blood vessels, we usually draw it kind of like this, right? You've got an artery, and then it branches off and it forms like what we call a capillary bed, because it's kind of covering a tissue, kind of like a bed of something. And then they kind of come together and they go to your vein. So you'll notice this is a great image, right? Like this is a great way to understand these. Arteries always travel away from your heart, and veins always travel towards your heart. Okay. Generally, we draw them in these colors, but there are some cases where they'll be flipped into different, whether they're oxygenated or deoxygenated. But for the most part, most of the arteries in your body are, being pumped away from your heart. So they're very, very, very oxygenated. And most of the time, veins are going towards the heart. They're very, deoxygenated because they just got done, dropping off all their oxygen. So now they have nothing but CO2, so they're traveling back to the heart.
Can you repeat this again, please? Most of the
artery, I'm sorry.
You was talking about most of the artery are more oxidated.
Yeah, most of the arteries are very oxygenated. Most arteries, in your body are coming from the heart, which means they have lots and lots of oxygen because your heart just pumped them out, going, to your various tissues throughout your body. And then most of your veins are deoxygenated, but there are exceptions. For instance, when it's traveling to your lungs, right, you have arteries traveling away from the heart to the lungs. That spot right there, they don't have any oxygen because they got to get to your lungs to get oxygen. And then the veins that are going back towards your heart from the lungs, in that case, they have a lot of oxygen. So there is an exception to the rule. When you're dealing with your pulmonary arteries and your pulmonary veins, it's flipped. But in most of the rest of the body, arteries usually have a lot of oxygen, veins usually don't. But that's not what's important. What's important is the direction. Arteries away from the heart, veins towards the heart. That's what you want to memorize. And then capillaries are the little exchange sites, okay? So here's what's cool, by the way. Take a look at this fun little fact. It is a systemic circuit of nearly 60,000 miles in your body right now. That is enough to go around the earth, I think, 2.5 times. Right? Let me see. Hold on. What is circumference of the earth? Come on now. 15 centimeters. What? Circumference of the heart? What happened? 24,000 miles. Yeah. So it is about 2.5 times around the freaking planet. Your blood vessels alone. How cool is that? That's how small they get. They get so tiny. They can become microscopic. In fact, your capillaries, which are the really tiny ones, are sometimes so small, they are smaller than your red blood cells. And it's like, wait. Blood's got to travel through the capillary. So how can the tube be smaller than the thing traveling through the tube? Well, in a minute, when we talk about blood, that's why red blood cells actually look like this. They're this little, like, you know, kind of filled in donut shape. Well, that's really easy to fold and really easy to bend. And so, you know, they can squeeze themselves through these little holes. That creates a little bit of pressure, and that gets your blood cells to travel to where they need to go. Another really cool, you know, design of our blood circulatory system. So, what are all these blood vessels responsible for? What do they do, right? Well, they're responsible for delivering oxygen to your body's tissues and picking up CO2 from those tissues and delivering them to wherever it is that they need to go. So blood will leave the left ventricle and it will get into the largest artery that you've got in your body. In my little drawing, it would be this little section right here, but my drawing sucks. So let's look up a real heart again. So the largest artery that you've got gets its own special little name. We actually call it the aorta. And so when your left ventricle pumps, it travels out right here. This little loop right here is your aorta, right? There it is. And it loops up around and drops behind the heart. I want to find a big picture of the aorta. I want to see where it drops. There it is. So you can see, like, it loops up and drops behind the heart. That's where it's going to split off and go to all of the different parts of the body. So this is your biggest blood vessel you've got. It's about as big as a garden hose. That's a pretty big freaking blood vessel. This is sometimes what they have to replace in certain people. Sometimes they'll replace this using like pig or cow aortas. Kind of cool, but anyway, arteries are traveling away from your heart, and they're your largest blood vessels. Eventually, that aorta is going to get smaller and smaller because it doesn't need to be quite so muscular the further away it gets from the heart. The further away from your heart, the lower your pressure is, right? And so, you know, once it's traveling fairly far away from the heart, it doesn't have to be quite so muscular anymore. So your arteries are going to get smaller, but make no mistake, your arteries are huge compared to your capillaries. So arteries are the largest blood vessels. Their job, they carry blood, and I underline this here, away from the heart, okay? Now, arteries will eventually have smaller branches. They'll get smaller and smaller and smaller. So we see arteries and arterioles. So eventually, you'll see they branch smaller and smaller and smaller. Let's take a look. That is a really tiny picture. There we go. So you can see an artery is pretty big, and then it branches off. And see how this one's just a little bit smaller? This is what we call an arteriole. You probably won't ever get asked a question about arterioles, but arterioles will branch smaller and smaller and smaller until eventually they become the capillaries. So remember yesterday we were talking about the lungs. You've got bronchi, which become bronchioles. Well, you've got arteries, which become arterioles. And those are really just tinier versions of arteries. They're still traveling away from the heart. But then your arteries, so you get an artery and it branches smaller and smaller. And then we consider it an arterial, and then it gets smaller and smaller. And then it is a capillary. And a capillary is microscopic blood vessels that form beds. And these are the actual exchange sites that cover your tissues. This is where you are trading oxygen for CO2. So when you look at like these capillary beds that are covering tissues, that's really where most of the nutrients are being exchanged, right? Like, hello, cell, let me give you some glucose. And it's like, excellent, I will use that glucose to produce energy. It's like, you know what, while I'm done, would you mind taking this CO2 for me? And then your blood cells are like, yes, I would. And then poop, they travel back to your heart, right? So they're trading everything off. They're dropping off glucose, they're dropping off CO2, and they're picking up, they're dropping off glucose, they're dropping off oxygen, they're picking up CO2. So I want to show you here, here's an even better picture, right? Veins are large, arteries are large, arterioles are small. Now, once you get to your capillaries, which are really small, capillaries are tiny, they're microscopic, right? They absolutely cover our tissues. They'll start to come together. See how this like branch, is coming together, and then that branch is joining with this branch, and then this branch is joining with this branch. They start to come together and they become what's called a venule. A venule is a small version of a vein. And then eventually all your venules come together and you're left with an actual vein. So veins are traveling back to your heart. So blood vessels that carry blood back towards the heart. So here's what you guys need to memorize.
One question, please.
Yeah, go ahead.
For example, when the person is checking the blood pressure and they pinch in the finger, this is in the capillary things. That's why it's coming the sugar.
Do you mean this one, like when you're doing this test?
When you pinch in the finger.
Yeah,
coming out the blood to check the sugar.
Oh, I'm sorry, not pricking the finger. Yeah. Sorry, there's like so many different medical tests out there. Yeah, so when you puncture your and you take the blood out, that is actually just so that you can get some blood, and you're doing a glucose test. You're just testing how much sugar is in your blood. What you're doing when you puncture that is you are ripping the skin, and you're exposing and you're breaking a capillary bed. And so blood is leaking out of your capillaries.
Oh, okay.
Yeah. And then, let's say you're donating, let's say you're like getting an injection, right? They will inject blood, they'll inject into a vein usually, because there's not very much pressure in a vein. Doctors are not going to inject into an artery, because if you were to inject into an artery, remember, arteries are really big, right? And arteries are traveling away from the heart. So if you think about that, right, they're big and blood's going away from the heart, which means that is right after the heart squeezed all that blood. So if you were to inject into an artery, what's going to happen is blood's going to come shooting out of your arm. And they don't want to do that. So they inject it into veins because it's traveling back to your heart. It's lost all of its pressure by the time it gets back to your heart. Okay. So that's why you inject on there. But in terms of the finger like prick, that's just because that's a low bleeding area and it heals very quickly.
Yeah, well, I was having that question because you was talking about the capillaries, and you were saying the capillaries have the nutrients. Said,
it's
where the capillaries have the nutrients and have something of the sugar. That's why they pinch. The doctors pinch the finger.
Yes.
The float and see how is the sugar and what.
Yeah. So that blood is actually, those nutrients are present everywhere in your blood. But yeah, you have a lot of capillaries in your finger. So that's where it's being exchanged. So it's just a great place to kind of test it. Actually, let's look at the blood vessels of the finger. You can actually see here. This is what they look like. You can kind of see. All these little blood vessels, and they're absolutely covering that tissue, which is why when you prick we don't want to look at that. That's why when you prick your fingers, There's just a lot of blood there. But it's also why, look at how small these little blood vessels are. They're very small here.
Mhm.
That is why your fingers get so cold compared to the rest of your body. The vessels everywhere else are a little bit larger. That's also why it's easy to get your finger to stop bleeding really quickly. And that's why they choose that spot, because it's easiest to stop the bleeding because the vessels are so small. Here's a fun picture, by the way. I just saw this and I wanted to show you guys. So there's like from your heart, there's the stuff going up to your lungs, right? And then there'd be other ones that go up to your brain. But see how like your artery branches off? There's like the upper body and then it branches and there's your lower body. This isn't what it looks like in your body, but you can imagine, like, look at all these different exchange sites, right? And then these are all, they're going to your different organs and stuff. So let's take a look at the size here. Look, oh, this is a really great one. Look at this. There's a big artery, right? And then it gets smaller and smaller and smaller. Now, if we look at the difference in size between arteries and veins, remember your veins, they don't have as much pressure in them, right? They don't have, this is, they go to a tissue, they drop it off, and now they got to get sucked back to the heart, which means the pressure in a vein is way lower than the pressure in an artery. So what you're going to see is that your arteries are much larger and their walls are much, much, much thicker than your veins are. Right. And so you'll see this. See how thick that wall is in an artery versus how thin it is in a vein. That thick wall has to deal with all the pressure, and that means it's not going to break. Versus a vein, which is actually meant to be pretty squishy, so that, like, if there's a lot of pressure moving through it, it is able to move very easily, because honestly, there just isn't very much pressure in your veins. And the other thing is, because there isn't as much pressure in veins, what you will also see, your veins will have valves in them. Your arteries don't have any valves. And so those little valves there are what prevent blood from backflowing when it's traveling through. So the pressure is really low. We don't want that to be traveling up and then like lose its pressure and then fall back down. So what'll happen is it will travel up, and then that valve will close, and then that blood cannot backflow. So it looks kind of something like this. You'll see, we'll see like a tube like this, and it'll have like a little valve like that and another little valve like that. And blood will travel this way, and then it cannot travel this way, right? I don't know. It can't backflow because it gets stuck. That was my worst drawing so far. But I think you guys get it. So arteries are the largest blood vessels. Again, arteries go away from the heart. Capillaries are microscopic blood vessels. That's where you exchange nutrients, oxygen, CO2, glucose, whatever, hormones. And then veins are traveling back towards the heart. And then veins have these special little valves that prevent them from backflowing. Now, there is one special type of artery in the body. They get their own little label here, and those are your coronary arteries. And your coronary arteries are actually the very first arteries that deliver anything compared to everything else, and they are what are traveling around your heart. So there's that aorta, right? That aorta is allowing blood to travel up where it needs to go. It's got a couple little holes in it, and those holes connect to these little arteries right here called your coronary arteries. Those coronary arteries split off. They split off like crazy, and they cover your heart's tissues. And that allows your heart to supply itself with blood. So your heart isn't just passively taking blood from the chambers, it isn't getting nutrients from the blood that's in the chambers. It's getting its nutrients by pumping right out and then coming around and surrounding the outer tissues of the heart. And then that will travel to, all throughout that cardiac muscle and give it all of the food that it needs in order to survive. So your coronary arteries are arteries that are responsible for providing the heart itself with blood. Now, those are the most important arteries in your body, hands down. Because remember, your heart is the pump that pumps blood everywhere. What do you need to keep alive? The pump that pumps blood everywhere, right? So we want to make sure that we never block our coronary arteries. We do not want to increase the pressure of our coronary arteries. And we're going to do that by making sure that we have a healthy diet and that we exercise. Because when you see a blocked coronary artery, what is going to happen is you can see maybe like cholesterol or fat builds up on the inside of one of those arteries. And now the pump, which is getting blood everywhere, now some of the tissue in that pump dies. It suffocates and it cannot pump blood throughout the rest of the body. Now the pump is not a pump anymore. It's just a thing inside of your body that's doing nothing. Right. And so you just had what is more commonly referred to as a heart attack. And now you can't pump blood to your brain. You can't pump blood to your legs, your lungs, whatever. Right. So, we do not want any of the cells in our heart to suffocate. That is why it is so important to not smoke. That's why it's so important to make sure that you have a healthy diet. And it's why it's so important to keep your heart strong through exercise, because you are going to make sure that there is never any plaque buildup on the inside of your heart. When someone does do that, what'll happen is, they'll have a heart attack, and a lot of times doctors will go in and they'll put in what is called a stent. And a stent is basically what they'll do is they'll thread a little balloon through, and you can see all the plaque. What they'll do is they'll inflate that balloon, and they got this little cage here, and it'll click open, and then it gets stuck in that open position, and that forces your blood vessel to stay open forever. That is how they, fix your heart after a heart attack. But, that doesn't really fix your heart, right? What fixes your heart is, again, diet and exercise.
And you get too much, though? Too much blood?
Nope. That one, Noel, I know the answer to real quick. Definitely not. You want as much blood flow as possible. I will say this. My mom, who had a heart attack a year and a half ago, my mom, when they first put her stent in, it felt like she got too much blood. So like she described, like right after her heart attack, her heart would start racing like crazy, and she'd be like, and she would get like really amped up, and she'd feel like she was like full of adrenaline. And that was because I was like, and she was like, it's scary. And I was like, I know it's scary, but that is just your heart getting oxygen the way that it was supposed to, rather than like what it's been used to for probably years. You've been building up this blockage for years, and so your heart got used to not getting as much oxygen. Suddenly you started giving it all the oxygen in the world, so your heart feels like it's racing. And it's it's like we used to own a pet store, so the way I described it to my mom, it's like a malnourished dog that finally got to eat. Of course it's going to be excited and run around like crazy. But yeah, no, you can't get too much blood flow. All right. So those are your coronary arteries. By the way, look at this statistic right here. About 33% of all deaths in the Western world are the result of coronary artery disease, blocked coronary arteries. Kills about a third of the population. It is the number one cause of death in the United States. The number one thing that kills us is heart disease, which is a very preventable disease. We just live in a very developed world with lots of access to poor food, that tastes good, but is not very good for us. We have access to tablets and TV and, computers, and we just sit around all day. We don't exercise. Even things like, you start looking at like, now I'm not saying I want to go back to like a pre-washing machine world or anything, but like you look at like how hard it was to wash your laundry back in the day. You used to have to like do a lot of work. You had to scrub it on a washboard, we don't do it anymore. Now you throw it in and you go watch Netflix. That is hurting our hearts. So we need to balance it out with exercise. Anybody in here ever used a washboard? My parents have one as a joke. I used to have to use it whenever I got in trouble. My
And
mom,
my grandma still uses that.
does she? Yeah, that was like my punishment when I was a little kid. If I didn't do my chores, like if I didn't do laundry, because that was like one of my chores when I was a kid. My mom would be like, "All right, well now you have to do laundry the old-fashioned way," and she like kept this old one, and I swear it was like busted. Like it didn't work very well. Like I was like, and she's like, it's supposed to be hard. And I was like, yeah, but I think one is even already worn out. And then that got me in more trouble. All right. So your coronary arteries, like I said, you've got your right and your left. Don't worry about memorizing these. These are just in here as information. But your right coronary artery arises from the right part of the sinus and supplies the right side of your heart, and your left coronary artery does the left side of your heart. So like we mentioned earlier, all of your heart signals are going to start with your SA node, right? That's going to generate, by the way, that electric signal has a name. We've been talking about the electric signal that your heart makes. It's called an action potential. So the action potential is generated by your heart at the SA node. That's your sinoatrial node, the pacemaker of the heart. And then it travels to the AV node where the signal is delayed for a second. Then it travels down the heart to your Purkinje fibers, which contract the rest of the heart. The heart finally squeezes all that blood out into your aorta, where it will travel through your arteries. Then it will branch down into arterioles. Then it will branch down into capillaries, and it will drop off all of its oxygen, pick up some CO2, and then that blood cell will travel back in from a capillary into a venule, which will travel into a vein, which will travel all the way up to the heart. And then luckily the SA node is going to beat again. SA node beats, that moves the heart, the blood into here, and then it will travel to your lungs where it will drop off its oxygen. And there we go. That is the traveling of a heart cell, right? I'm sorry, a blood cell. That is how your blood cell travels throughout your body. That's the life cycle of a blood cell. So now let's go ahead and move out of all that anatomy stuff. Let's move out of anatomy and let's look at, performance here. Let's talk about like, all right, well, what does that mean for us? Like during a session, what's happening to our heart, right? Well, we got to look at matching the idea of your coronary blood flow to your oxygen demand, right? So how much oxygen do you need? That's going to determine how much your heart beats, right? If I'm sleeping, my heart rate is real low because you know what? I'm not using that much oxygen. My body's like, pretty easy to get blood to wherever it's going. I'm laying down. I'm not really working all that hard. My cells are like, yeah, we're not doing that much work. We're not consuming very much oxygen. But then I start to get up and maybe I go for a morning jog. And now my heart's going to start beating faster because my cells are using more energy, which means they need more oxygen to spit out more energy, right? They bring in that oxygen, they spit out energy, and they spit out CO2. And I need to get rid of that CO2. So I need to exhale it. So my heart's going to start beating faster, right? So compared to skeletal muscle, 40% of your cardiac cells are made up of mitochondria. This is consuming most of your heart actually consumes more oxygen than skeletal muscle does. But skeletal muscle, you've got way more of it. So, it's really eating a lot of that stuff. And all of this, the speed of your heart rate is controlled by your nervous system. It's controlled by what we call your sympathetic nervous system. That is your fight or flight nervous system. So the more work you start doing, the more your nervous system is going to start beating faster and faster and faster and faster, right? Because your sympathetic nervous system is going to make, what did we talk about earlier? Adrenaline. It's going to make cortisol. It's going to make stress hormones. And your blood is getting more acidic because it's got more CO2 in it and it's got less oxygen. All of those things coming together and your brain saying, all right, we are running, we're doing exercise, we're working out, we're lifting weights. All of that information coming together is telling your nervous system to zap your heart a little bit faster. And so your heart's going to pick up its pace, right? So oxygen consumption in your myocardium is higher at rest is higher than skeletal muscle. Your heart is consuming a lot of oxygen compared to skeletal muscle until you start doing rest. Like when you're at rest, your oxygen is, your heart is consuming a lot. But then you start working, right? And now all of a sudden your skeletal muscle starts, really doing a lot of work. So now your heart is going to start pumping faster. And so we can calculate that. We can calculate that. We call that your cardiac output. It's the overall performance of your heart. And some of this is based on this basic physiologic principle. We call it the Fick principle. Don't worry, you don't need to know that term, but it's used to calculate your cardiac output. It's the total oxygen consumption divided by the oxygen content in your blood. Basically, what the Fick principle states is as there is less oxygen in the blood, your body knows that it's because that oxygen is getting burnt up for energy. So that means that your heart will know that it has to beat faster. The more work you do, the faster your heart beats. That's a much simpler way to explain it. So that is where your SA node is now going to get the signal to start pumping faster. And so the sinoatrial node, the pacemaker of the heart, will generate more action potentials. When it's at rest, it's around 70 beats per minute. That's an average resting heart rate for most people. Now, I'm going to say that right now. You guys in here have probably noticed that your resting heart rate's like right now, I'm upright and I'm talking and I'm moving my arms a lot and I'm kind of animated. And even right now, my heart rate is around 73 beats per minute. So that's almost as if I'm at rest. That's because my normal resting heart rate is around like 58 beats per minute, which is lower than what they're saying here at 70. You guys are probably the same. Most of the people in this call, we're all here to study exercise. You guys probably all exercise pretty regularly. So I want you to remember the average resting heart rate is between 70 and 80 beats per minute. That's the average. You will notice yours are probably lower. Maybe not, but more than likely. I just don't want anybody to be like, mine is no, and then, forget what numbers you're supposed to remember. Now, there are things where like your heart could be really slow. If your heart's beating really slowly, we call that bradycardia. If your heart's really beating really fast, we call that tachycardia. Both of those are really bad as well. But generally, it's around 70 to 80 beats at rest, and then it goes up as you start to exercise. And then pulse pressure, we don't need to worry about that. Actually, we can skip the Frank Starling law. Yeah, and here's just a diagram of like how all of that is happening. Your brain's nervous system is going to travel down your spinal cord, and it's going to activate your SA node, which will travel to your AV node, which will travel to everything that we've been talking about now. So what happens if you start exercising? What kind of effect is that going to have on the body? Well, rest and either submaximal or maximal exercise, so either like working at a level below high intensity or working at a level at high intensity, both of those things are going to increase your parasympathetic nervous system's activity. So you are going to trick your body by exercising into fight or flight mode. By exercising, your body, if you go to the gym, your nervous system doesn't know that when you pick up that barbell, you're not fighting a bear. You're still like this biologic creature that, is a cave person at the end of the day, right? And so like when you go to pick up like dumbbells, start doing bicep curls, it thinks that you're fighting like wild raccoons and bears and lions and tigers, it thinks that you are in danger, so it activates your fight or flight mode. And that is what increases your heart rate, because your body's going to go, oh, wow, we're doing a whole lot of work here. And what's really cool is, certain parts of your body actually will shut down while other parts of your body activate. So for instance, when you start exercising, and here's this is a very personal question for you guys. I don't know if you've ever taken note, but you ever noticed how when you're in the middle of a workout, especially if it's a hard workout, if you're doing like a boot camp or something, you don't really have to go pee. You don't really have to go to the bathroom. You ever notice that? Kind of a weird question, I know. But if you've noticed that, there's a reason for that. When you are doing lots of work, your digestive system, for the most part, it kind of shuts down. It really doesn't do very much. Your body kind of stops processing food, just kind of lets it sit around for a little bit. Obviously, it's doing a little bit of work. It's not like those tissues are getting no oxygen, because if they got no oxygen, they'd be dead. But for the most part, they're getting less oxygen, and your body will prioritize getting oxygen to whatever part of the body it needs to go to. So it'll expand the oxygen to, let's say, your legs, right? You go for a run, your legs are going to start getting most of the oxygen. Your digestive system is going to get less. So your body will expand and create greater blood flow wherever it needs to go. We actually take advantage of this. Noel, Nicholas, Charlie, you guys will recognize this when I say it, but we actually do this specific type of working out with clients who have blood pressure problems. I'm going to teach you guys how to do what is called a peripheral heart action circuit. In class, actually, we're going to do some of those when we meet on Monday. And what a peripheral heart action circuit is, a circuit training, right? It's doing a bunch of exercises in a row. Okay, so squats into lunges, into bicep curls, into tricep extensions, into a shoulder press, into a deadlift, right? Boop, 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 in a row. That's a weird workout, but don't worry about it, right? If you're doing this all in a row, right? And you didn't rest, you just did one, then the other, then the other, then the other, then the other, right? Well, you know what? That's a circuit because you didn't take any rest. But what if I rearrange stuff instead? What if I did squats and then I did some push-ups and then I did some lunges and then I did a shoulder press and then I did a deadlift and then I did a bent over row? So I'm going to go from legs to chest to legs to shoulders to legs to upper back. Up, down, up, down, up, down. Oh, lower body, upper body, lower body, upper body, lower body, upper body, right? I think I just had my hands backwards. Don't worry about that. Oh my God. All right. So anyway, lower body, upper body, lower body, upper body. So that's a peripheral heart action circuit. And what that does is it evenly distributes blood throughout your body. Because what you do the squats, your body opens up the blood vessels to your legs and it closes the blood vessels everywhere else. Then you start doing push-ups and it opens the blood vessels to your chest and it closes the blood vessels everywhere else. So what you're doing is you are opening and closing, opening and closing, and opening and closing your arteries. And what that does is that sends blood back and forth. You are literally it's like doing reps for your blood vessels, right? You're doing reps.
But I have a quick question.
Yeah, sorry. Please, what's up?
Yeah, is that like doing, like, let's say, because I've been trying this and it's like a pull push workout. So one day I would do let's say pull workouts for lower body, and then at the same time I'm doing upper body, but I'm doing push workouts. So it'll be pull push. So
you're doing like I do deadlift plus a chest press, right?
Yeah, or like a trap bar deadlift with push-ups.
Love that. That's a great pair. So yeah, that is exactly what's happening. So when you do the trap bar deadlift, blood's going to your legs. And then you do the push-ups, blood's going to your chest. And so you are sending blood back and forth. You are doing what I like to do. You're doing the zigzag. So you're going lower, upper. And then on your other day, I'm assuming you're doing lower, upper, right?
Yeah, the next day it would be lower body, let's say like squats, some lunges, and then I would do or goblet squats, front squats, and then I would do pull. So like I would do a bent over rows, upright rows.
Yeah, that's like that's the zigzag. I really like that version too. That totally works. That's peripheral heart. If you do it as a circuit, so like 2 or 3 exercises, 4 to 5, 6 exercises in a row, that's peripheral heart action. If you're just doing it as a pair, so let's just say you do like one, then the other, and then you rest, it still does a little bit. It's just not doing as much.
Got it. Yeah, because I do one and the next one. It's a circuit, and then at the end of my workout, then I just I'll take like a minute break, and then I'll do it again. I'll repeat it like four times actually.
Yeah, that's great. If you had high blood pressure, that is the type of workout I would give you. Clients who have blood pressure problems, peripheral heart action circuits are like our #1 tool. They are incredible at helping with blood pressure problems because you train your blood vessels to get better at, constricting and relaxing, right? We get them better and better and better at, doing those movements. So yeah, Charlie, that's great. You don't quite have to do it that way if you don't want to, just so you know you have options. You can keep doing the cross where you go upper, lower, upper, lower. You can also just do like upper, lower on this side and upper, lower. You could do like chest and quads and back and hand. That also works. You can do anterior chain, posterior chain. Both work. They're, just so you know, you have options in the future. If you ever want to change up your workout,
yeah, got it. Thank you.
Just flip them. Great question. I love that. And my newbies, you guys are going to experience this in just a little while. So if a lot of that sounded like Latin, it'll make sense in no time at all. Trust me. All right. So let's say you start doing some endurance work, right? Let's say you start doing, cardio training, right? Well, your body is going to get better at delivering oxygen throughout the entire body. And so when it comes to cardiac output and you're calculating how your heart is working, right? Cardiac output, like I said, it's the overall performance of the heart. It's made up of two main things here, right? Oh, actually, hold on one second. I got one last thing to mention here on the slide. At rest, you don't have very many stress. When you're resting, you don't have very many stress hormones running through your body. So because you don't have very much stress, your heart rate is going to be very low. When you are at high stress, your heart rate goes high. And you can see it here. It mentions that, where is it? Like your kidneys, right? Your kidneys are removing certain like metabolic wastes. Your kidneys are also generating that adrenaline. They're sort of responsible for, picking that, creating the hormone that picks that pace up.
What's that acid that be in the muscles as you develop, you try to develop working out?
Lactic acid.
Lactic acid. Yeah, lactic.
Yeah, so that's the byproduct of metabolism. The more work you do, the more lactic acid as a byproduct you're going to have. So cardiac output.
6 months.
Yeah. Wait, what's that? So cardiac output, the overall performance of the heart. There are two sides to cardiac output. Two sides. There is the number of times your heart beats, and there is how much blood is being pumped per beat. Okay, so it's made up of your heart rate, that's the number of beats per minute, and your stroke volume, the volume of blood pumped per beat, right? And so, like I said, heart rate, the number of beats in 1 minute, stroke volume, the amount of blood ejected by the heart per beat. Now, here's the thing. Stroke volume is really important, but we can't calculate it. We can, we just need like a lab in order to do, you need to be in like a doctor's office. So trainers, we don't have these big sophisticated tools to be able to calculate how much blood is being pumped every time your heart beats. Like if I've got like Andres doing a bunch of squats, right? I can't tell how much blood his heart is beating every beat. But what I can do is I can measure his heart rate, right? And we know that the overall performance of the heart is related to how much the heart is beating and how much blood is being pumped. So if you are not pumping very much blood per beat, what do you guys think is going to happen to the rate of the heart?
What was that again?
If not very much blood is going through the heart every time it squeezes, like if it makes a really weak squeeze, what's going to happen to your heart rate?
Going to be low?
Is it going to drop?
No, it's actually going to go the other way. It's going to speed up. So here's the thing. They are backwards of each other. So stroke volume. God dang it. I changed the default.
Is that because it's going to try to pull more blood towards through it?
Yes, it's got to find another way to get blood to travel, right? Because it's not getting it per beat. So stroke volume, right? We're going to give this a definition here. It is the amount of blood pumped through the heart per beat, okay? That's your stroke volume. Your heart rate, right? That is the number of times the heart beats in 1 minute. So if your stroke volume is low, your heart rate, has to be high. Your heart rate is going to have to increase. These are going to work backwards of each other. Because think about it. Let's say I need to move. I've got 50 5-pound dumbbells over here, right? I bought 50 dumbbells online. I've got 50 of them over here, 5-pounders, right? If I'm pretty weak, it's going to take me a long time. I'm going to have to make a lot of trips, right? Let's say I can only pick up 2 dumbbells at a time. I got to make 25 trips in order to move them down the hallway, right? So if I'm really weak, I can't carry very much weight. If my heart's really weak, right? If my stroke volume's really weak, I can't pump very much blood per beat. So I have to beat more. I have to do more trips, right? So if I'm really strong, let's say I can carry 10 dumbbells at a time, right? It's only going to take me 5 trips. So I only have to take 5. So if my heart's really strong, my heart has to beat less often. Does that make sense, everybody?
No.
Everybody clear?
Not yet. No.
Not yet?
Yes.
Okay. So let's put this up here. So cardiac output is the overall performance of the heart, right? So your cardiac output is the overall performance of the heart, and it is your heart rate or your stroke volume times heart rate equals cardiac output. Okay. So that's what you need to remember. This little, almost this little formula right here, right? So cardiac output is stroke volume times your heart rate. So if my stroke volume is low, my heart has to beat more often. And that is why, okay, let's look at it another way. Let's say, I decide to race, we'll say Kenny, right? Kenny, you're brand new. We're going to break you into the program and you and I are going to have a race.
Got you.
All right, so I gotta warn you, I love cardio. So you and I are gonna run a mile, okay? But it's not gonna be a traditional race. It's not going to be a race where you and I run the mile as fast as we can. Instead, we're both gonna get on a treadmill, and we are both going to set that treadmill to 7.5 miles per hour. That's a pace that's not too fast, right? Should be able to keep that up for a full mile, right? So we do we both get on this treadmill and we both do, we both do 7.5 on the treadmill. We both are going the same pace and we are both going to do the same distance, and it is going to take both of us the same amount of time. Now, do you do a lot of cardio?
Yes, that's what I do. 7.5.
You're running?
correct.
I love it. That's good. All right. Well, you know what's going to happen? Whichever one of us had an easier time, we're going to get off that treadmill and we're both going to take our pulse and we're going to measure it and we're going to see how many times our hearts beat in 1 minute. And maybe you absolutely crush me. You do your heart rate and it comes out to, in that 1 minute's time, let's say it comes out to 130 beats, right? And then I did mine. We did the same pace. Mine came out to 150 beats. That means that you beat me by 20 beats. Your heart is in better shape than mine. Does that make sense?
Yeah, makes sense.
Soraya?
Yes. Okay, I got it.
Cool. So that is why if you have a weak heart, it has to beat more often. So we can't measure the stroke volume. We don't have the tools while we're in the gym. But let's say you have a client, let's say Kenny, actually, we're going to go back to our analogy. So we had this race, we're going to do it today, right? And then I get ticked off. I got defeated. So I'm upset. So guess what I'm going to do? I'm going to train like crazy. And in 30 days, we're going to have another race, right? So then I start running every day. I start training, I eat really well, and I really train for this event. And I come back and you beat me again. But this time you had 130 and I had, instead of 150, 140. So I had a 10 beat improvement. That 1 mile wasn't as hard as it was the first time. I'm getting a little bit better, right? That is how, this is one of the reasons why we keep an eye on our resting heart rate. We want to measure our clients' resting heart rate and say like, hey, your resting heart rate's really low. That shows me that you're in really good shape, right? Or, hey, I put you through this stressful activity and your heart rate was this at the end. The first time we ever did it, we've been working together for 6 months. We did the same test today. Your heart rate's way lower. That shows me that your heart's getting stronger. And that's how we look for improvement. Does that make sense, everybody?
I didn't know that your heart could get better with time. I didn't know.
Oh, yeah. It actually gets better because your cells actually get better at consuming oxygen and your heart gets better at pumping blood. Yeah. So cardiac output. And by the way, one last little thing I want to show you guys on my little chart that I'm drawing here. Stroke volume times heart rate equals cardiac output. Most of the time, you guys will see this formula written like this: SV times HR equals, and it'll be listed as Q. Why is it not just CO? I don't know why, but they really like to use Q. Q stands for quotient, but a lot of times you'll see this formula, and that is representing this. So there's two sort of ways you need to memorize the definition of cardiac output. You either memorize it as the overall performance of the heart, or you memorize it as your heart rate times your stroke volume. They will ask you either version, so you need to be prepared for both. Okay. All right. So your type 1 fibers, when we look at that, right? Type 1 fibers. And by the way, Kenny, you said you didn't, you're like, I didn't know the heart could get better, right? Well, part of that is, adaptation. Part of that is your body getting better at cardio. It's not just your heart, it's your entire body. If I start running regularly, guess what? My legs are going to develop more of those type 1 fibers that we talked about, those endurance fibers. My legs are going to make more capillaries. They're going to make more blood vessels to my legs. My legs are going to make more mitochondria, and it's going to make more myoglobin. And all of those things are going to make me better at delivering oxygen to my legs. If I get better at delivering oxygen to my legs, I'm not as likely to use as much oxygen. I'm not as likely to get exhausted quite as easily. So, it's not just the heart getting stronger. It's also the rest of your body adapting, which is what's so cool. I love cardio. Now, one last little thing. Actually, where is VO2 max? Oh, it's at the very end. So one last little thing I want to mention is your blood's pressure as well. We kind of talked about it when we were talking about those workouts with Charlie. Charlie was talking about the peripheral heart action up and down workouts, right? So blood pressure, this is the amount of pressure inside of your blood vessels, right? And so there are two versions of blood pressure. There is your systolic blood pressure, that's known as your systole, and your diastolic blood pressure, which is your diastole. Okay, systolic blood pressure is the pressure pushing on your arteries during a heart's contraction. So when your heart squeezes, pressure is really high, right? And so the pressure is going to be around 120 in a healthy heart. When your heart relaxes, that is your diastole, the pressure pushing on the walls during the relaxation of the heart. So your heart's squeezing and relaxing and squeezing and relaxing. That's pushing blood through your arteries. So if you take that blood pressure cuff and you put it on this brachial artery, actually you do it on the left arm. You put it on a brachial artery here on the left arm, right? And that little blood pressure cuff is going to measure how much pressure is pushing on the cuff when your heart squeezes and how much pressure is pushing on the cuff when your heart relaxes. And that typically is, in a healthy heart, 120 over 80. Now, if it's 140 over 90, that is where we consider you to have high blood pressure. So your heart is squeezing, and unfortunately, there's something in your blood vessels blocking. And it's kind of like you guys know when you're like watering your plants in the garden or whatever, if you've ever used a hose and you take your thumb and you put it over the hose and it causes the water to shoot farther, that's because you're creating pressure. You're closing up some of the hole, so more pressure, right? Well, you close up some of the hole in your blood vessels with like gunk, plaque, right? Cholesterol, and it starts building. Now your blood pressure is going to go up. And that's not good, because that means that is now if you've got high pressure here, what does that mean somewhere else? You got low pressure somewhere else. So now suddenly it's hard to get blood to travel around your body. And that's why hypertension is so dangerous. Because if you have high blood pressure, it can cause things like blood clots. Your blood can start pooling, and then it starts to clot together, and you get basically a scab inside of your blood vessels. And then that could travel to a really small artery or maybe a really small vein. And what happens if it gets stuck? If it gets stuck, now you've got no blood traveling, right? And now suddenly the tissues in a certain area are not getting any blood. No blood, no oxygen. No oxygen, no life, right? And that's what a heart attack is. That's what a stroke is. It's no blood to the heart, or it's no blood to the brain. Or sometimes it's no blood, you'll get neuropathy. Sometimes it's no blood to your fingertips or toes, So definitely something we don't want to have happen, right? So we want our blood pressure to be around 120 over 80. Now, like I said, training your heart, cardiovascular exercise will increase your heart's efficiency by primarily developing more type 1 fibers. Your type 1 fibers are the muscle fibers that have a lot of mitochondria, and they have a lot of oxidative enzymes, and they have a lot of myoglobin. And so they metabolically rely on your mitochondria, and they rely on oxygen, rather than type 2 fibers, which rely more on glycolysis and glucose. Both are good. Both are good. They're just used for different things. We love type 2 fibers. We love type 1 fibers. They're both great. And so through extended duration of exercise, your body, the more you do like long exercise, like go for a run, right? Or just do like high repetitions, like long sets, boot camp style training, your body will create more oxidative enzymes. And that's how, in 30 days, I got better at our 1 mile race. I created more enzymes, I created more myoglobin, I created more mitochondria, more blood vessels. And so my body got better at that. Rather than, let's say I start doing some heavy lifting, well, then I created more muscle tissue, I created more cytoplasm, and I created more glycolysis. Both are good. Both are good. Just depends on what type of athlete you want to be. They just have really, they're both good things. They just have different effects. So when we look at cardiovascular exercise from the perspective of our last little conversation here, which is your VO2 max. Now, here's the thing. There is a point where you are not going to be able to consume any more oxygen. Remember, you're bringing in a lot of air, which has a lot of oxygen in it. Your blood cells can only pick up so much of that oxygen. They can't pick up all of it. And that is where we start to end. And also your cells, you only have so many mitochondria. You only have so much myoglobin. Eventually, your cells just aren't going to be able to get enough oxygen. So you are going to hit what is called your VO2 max. That is your volume of oxygen consumed at maximum. It is the maximal volume of oxygen consumed by the body. As your intent, like right now, my VO2 max my VO2 is really low. But if I got up and started doing burpees right now, jumping up and doing my burpee and jumping up and doing my burpee, right? And I really start like getting super, and I go really, really fast. Eventually, as the intensity climbs, the volume of oxygen that I'm consuming is also going to climb. My muscles are doing more work. They're outputting more energy. They need more oxygen. But eventually, I'm going to hit a tipping point. You know, I've only got so many muscle cells. I've only got so much mitochondria, and my blood cells can only carry so much oxygen. So what's going to happen is as I start doing more and more and more work, I'm going to start consuming more and more and more oxygen, right? So, you know, that is where I'm getting a higher volume of oxygen consumed. So we have this concept called the respiratory exchange ratio. It is the ratio of oxygen consumed versus the amount of oxygen present in the body. Okay, so it's the we can think of this as oxygen consumed versus carbon dioxide expired. So let's say I'm sleeping, right? I'm laying on the floor right here. I'm asleep. My body's doing very, very little work, but it still needs to keep my cells alive. So oxygen comes in, about 70% of it gets used, and then I exhale 30% of the oxygen that I brought in. Not all of it. Oh, hold on. Wait, my internet's dying. 1 second. Can you guys hear me?
Yes.
Sorry, my internet was crapping out for a second. So I'm sleeping. 70% of my oxygen gets used. 30% of it does not. And then I get up, and maybe I'm at 73%. I start walking around. I'm at 75%. I start doing some push-ups. I'm at 80%. I start doing some push-ups plus some jump rope. I'm at 90%. I start doing some push-ups plus a jump rope plus a sprint. Now I'm at 100%. All of the oxygen coming in is getting burnt up, and the only thing I am spitting out is CO2. I'm leaving no oxygen behind. I'm using all of it. So what happens if I keep trying to do even more work? Too bad. I haven't got enough oxygen to do any more work. I'm using it all. So I'm tapped out, right? And that is where the ratio of oxygen consumed versus the ratio. If the oxygen comes from the body, 70% of it is consumed by the body's cells. That means that I'm at a ratio of 0.7. My respiratory exchange ratio at rest is 0.7. My respiratory exchange ratio at a full sprint, working as hard as I can, is 1.0. So let's draw another chart here, right? Let's say this first one represents intensity. So intensity, as intensity climbs, right? Intensity goes up. Well, the volume of oxygen consumed is also going to go up. I'm doing more work, you know, I'm consuming more oxygen. And my volume of CO2 is going to go down, right? I'm getting rid of, oh wait, sorry, other way around. My volume of oxygen CO2 expired is also going to go up. So intensity climbs, oxygen consumption climbs, CO2 exhaled also climbs, right? So that's my VO2 max in a nutshell, right? I'm going to exhale more CO2. So now the ratio is going to be different, right? So at rest, my respiratory exchange ratio is going to be 0.7, right? So that means that like I am consuming, so that's O2 consumed equals 70%. And my CO2 expired equals 30%, right? So So that is at rest. Okay, so that's a pretty, you know, that means that I'm working pretty gently, right? But then I have got during maximal work, right? Actually, we'll say at maximal work, at maximal effort. There we go. My respiratory exchange ratio equals 1.0. Okay, so now, and when I'm at full maximum effort, my O2 consumed equals 100%, and my CO2 expired equals, oh shoot, god dang it. I kind of set this chart up wrong. I walked myself into a corner here, actually. What I meant to do was shoot. This should be oxygen in both cases. That's why this chart was backwards. I was wondering why I didn't have my arrow in the wrong way. Hold on just a second. I want to talk about oxygen that is exhaled. The amount of oxygen consumed is the same as the CO2 expired. Actually, no, we can keep that here. Let's look at volume of oxygen expired. Okay, so how much oxygen are you exhaling? That is what goes down. There we go. I meant to put that up here. So then we got to put that here. Volume of O2 expired equals 30%. And this needs to also be 70%. Sorry, guys. I make so many charts and so many of them look certain ways, I sometimes fall for the patterns. Okay, so the oxygen consumed is 70, therefore the CO2 exhaled is 70. But the amount of oxygen that you are getting rid of, you didn't use 30% of it when you're at rest. But here, it's going to match up as 100% and 100%. And the volume of oxygen expired equals 0%. Oh. There we go. So that's what we want to see, right? So if intensity climbs, oxygen consumption climbs, CO2 expiration climbs, oxygen expiration declines because you're consuming all of it, right? So at rest, it's around 0.7, and at full effort, it's around 100%. So we are constantly in some shaded variation between 70 and 100, right? You know, generally working out is around 80%. If you're doing like a gentle workout or like a regular, you know, just a regular lift. But if you go into like a hard lift where you're like really sweating, you're working really hard, you might be as close to 90%. And if you do sprints where afterwards you're like, you know, you're really just breathing like crazy, that is, you're at one, you know, the reason you're breathing so hard is because you're using all of the oxygen. The only thing coming out of your body is CO2. This is one of the tricks that they actually tell you. Does anybody in here have a CPR card? Soraya, I know you must, based on what you were, you know, all this other stuff that you've done. But anybody in here have CPR?
Yes, I have.
Anybody else? No? Okay.
Say it again?
Do you have CPR?
Yes, I got it from MT.
Oh, okay. So you guys might remember, and the rest of you, you're going to get CPR. It's part of the Sochi program. We will give you CPR. But here's what's kind of funny about CPR. You might remember one of the things that they tell you when they are teaching you CPR, if there is a second person present, it is a good idea for you to alternate CPR. You should do the pumps, and then the next person should do the pumps, and then you should do the pumps, and then the next person should do the pumps. You actually alternate back and forth between the two of you. You know why they have you do that? Is because you are doing rescue breaths. And when you do those rescue breaths, if you're working really hard and you're doing more and more and more pumps, you start to get tired and you start to exhale less oxygen. And that means that you eventually, let's say you're working really hard, you're working up a sweat trying to keep this person alive. That oxygen that you're exhaling has mostly CO2 in it after a while. And that is why you actually alternate back and forth between the two of you. Hopefully that helps you understand. How you guys doing on respiratory exchange ratios? I kind of mucked it up in the middle there, but you guys understand that? Anybody have any questions at all? Feeling good, guys?
No, I'm fine.
Okay. I goofed it in the middle there, so now I'm nervous. Your VO2 is the volume of oxygen consumed. Your VO2 max is the maximal amount of oxygen consumed. Now, if you create a lot of red blood cells, you create a lot of hemoglobin, you create a lot of mitochondria, you create a lot of enzymes, you create a lot of myoglobin, you get all these things, and you have more muscle tissue. You start doing all these things. You start working out regularly. That means that you will have a higher VO2 max than you did before because your cells will get better at consuming more oxygen. That's one of the best ways to determine how good a shape, quote unquote, you are in, is how high your VO2 is. So we want to train, the more you train to develop your VO2 max, the more you are training to increase your power output by your cells, the more energy your body can create, right? So the more muscle you have, the more enzymes you have, mitochondria, blood vessels, blood, all of that means that you can create more energy than maybe somebody else. And that means that you're in better shape. And that's why, we can use your heart rate to determine how good of a shape you're in. But we can also, if we've got the equipment for it, we can measure your VO2 max. Now, for the record, measuring your VO2 max is pretty technical. It requires a very special machine in order to do that. You'll see like a VO2 max test. And it's actually this machine that you run on. And this machine is testing how much oxygen is going in versus how much CO2 coming out. It's measuring your respiratory exchange ratio. If you guys ever get a chance to do this test, I recommend it. It is a brutally difficult test, I'll warn you. It is very hard because you have to get to maximal intensity. You have to get to a point where the machine goes, that's it. We are, only CO2 is coming out. No oxygen's being exhaled. That's your VO2 max. And what'll happen, you don't see it here, but she's also wearing a heart rate monitor. And so what's cool about that is, if you do a VO2 max test, you can tell how much oxygen you're consuming when your heart rate is, whatever. If your heart rate's 120, maybe you're consuming 75%. If your heart rate's 150, maybe you're consuming 90%.
Oh, what happened?
That's me.
Is that a fire alarm? Sound like a fire detector went off.
Okay, sorry about that. There's a fire in the studio. Okay. We are right at the end here. Let's go ahead and finish this up. So when we talk about your cardiovascular system, you know, the whole point of it, it is an oxygen transport system. It is designed to keep your cells alive. Now, the efficiency of your heart, how well is your heart, you know, doing this job? Well, that's going to depend on, you know, your stroke volume, how effectively you can pump blood, but it's also going to rely on your blood cells, your muscles, and things like that, which are going to consume all that oxygen. The more oxygen you can consume, the higher your VO2 max is. That tells me that you've got a very in-shape body that can do a lot of work. And there's some formulas here at the very end of the PowerPoint. You're going to see those. Don't worry about those. You're never going to get asked questions about how to calculate those really, really complex chemistry formulas. They're just in there. I don't know why they're in there, actually. But don't worry about those. The last like 3 or 4 slides on this PowerPoint, I just don't take them out because NASA put them in there. But like, don't worry about those. They're chemistry formulas to calculate, you know, lactic acid versus how much oxygen and stuff like that. That's so funny. That alarm, it killed us like right as we were done. That is it for today. Any final questions? What are you guys worried about? VO2 max, definitions, arteries versus veins, ventricles versus atriums. Any questions, comments, or concerns?
Well, for me, again, it's like it is too much information about anatomy, and I want to know. Maybe after with you, you can tell me what's the. I know that everything is important because it's connected one with other. But for what we want to study, what is the more important?
Yeah, the biggest things I would say: memorize arteries versus veins, atriums versus ventricles, capillaries is a big one. Cardiac output, that's going to be heart rate and stroke volume, and VO2 max. Those are the most important terms for the day. Oh, and sinoatrial node. That's a big one. Make sure you guys know what the SA node is. So Roya, if it made it into the notes, that's the important stuff, you know? That's one of the things that the notes are for. The notes are basically my way of filtering out, like the PowerPoints have way too much information. The notes are meant to filter out the importance. They're meant to filter in the important stuff, okay?
Mm-hmm.
So just study your notes and it'll have, you know, everything you need. But we're going to go over this information again and again and again and again. So if you don't feel like you're an expert today, that's okay, because this stuff is going to come back over and over and over and over. Trust me, we've got 9 months. And I know that's hard to believe and you don't have any reason to trust me yet because we just met each other.
No, well, my concern is because I want to understand since the beginning. Because after going to come something more complex, right?
This is about as complex as it gets.
Oh, okay.
Yeah. But eventually the perspective is different.
Okay. Yeah, because well, what I see in other cases when I was studying, first it started with something simple and I start with after with something more complex, and if you don't have the basis in the beginning, after one will be more complicated to understand the rest.
You know, it's funny, Sochi's a little different than that. Sochi, instead of doing simple and then building up to complex, and then you're just expected to remember simple forever, we're actually more like loops. We actually like to make loops instead, and that way we revisit stuff. Because guys, you're going to work as trainers, you know what I mean?
Mm-hmm.
That means you're going to get the same questions all the time from different clients. So it's going to be very circular in your jobs. And we want to make sure you know how to revisit. We don't want you to forget the basics. So it's all meant to be, you know, revisited over and over and over again.
Okay. Thank you so much.
Any other questions today, guys? Anybody?
Nothing else.
Very good.
All right, guys, let's end the recording. I'll see you all tomorrow.